Hello, and welcome to The Sleepy Scientist. If you're here, chances are you're winding down, cozy under the covers, maybe with your eyes already growing heavy. Or perhaps you're just looking for a little quiet wonder before sleep. Either way, you're in the right place. Tonight, we're going to drift gently through the invisible threads that hold the universe together. Not stars or planets or particles, but something even more fundamental. Rules. Not the kind your teacher enforced or your cat ignores, but the quiet, mathematical laws that shape everything from light to life itself. Now, I do hope this video doesn't turn out to be too interesting. If it does keep you awake, at least you'll come away with a few cosmic truths tucked into your pillowcase. And if it gently lulls you to sleep instead, well, that's a win too. Before we begin, I'd love to know, where in the world are you watching from? And what time is it for you right now? Let me know in the comments. It's always a joy to see this sleepy little community stretch across time zones. And if this journey through the silent elegance of physics brings you a moment of peace, I'd be ever so grateful if you left a like or even subscribed. It helps more curious minds find their way here. Now, get comfortable, let the day fall away, and let's begin our quiet voyage through how physics wrote the universe. This video is intended for educational and entertainment purposes only, and is not a substitute for medical advice. Please consult a healthcare professional for any sleep-related concerns. Before anything existed, before time, before space, before particles had even the faintest idea they might one day exist, there was, as far as we can tell, nothing. Or was there? Nothing is a deceptively slippery word. To us it usually means the absence of stuff. An empty room, a blank page, a fridge you swear had cake in it this morning. But in physics, nothing is a much more complicated creature. It's not just a vacuum, not just the absence of matter, but the absence of space itself. No dimensions, no time ticking, no quantum foam bubbling beneath the surface. Not even a surface to begin with. This presents a rather puzzling question. If there was truly nothing, how did anything, laws, matter, energy, the very stage of space and time, come into existence? One might imagine the universe bursting into being like a magician pulling a galaxy out of a hat. But the trick only works if there's a hat to begin with. And in our case, there was no magician, no stage, no audience, just nothing. Or was there something? You see, modern physics doesn't have a unanimous answer. Some theories suggest that the universe didn't begin from absolute nothingness, but from a state we might call quantum nothing, a sort of vacuum that isn't empty in the traditional sense. Instead, it's more like a simmering pot of possibility, full of potential energy, and governed by the probabilistic twitching of quantum fields. Even in what we call a vacuum, particles can spontaneously appear and vanish, like fleeting whispers of reality that never quite commit to sticking around. This strange behaviour is a consequence of the Heisenberg uncertainty principle, which allows energy to fluctuate over short timescales, and these fluctuations, as odd as they sound, might have helped trigger the birth of everything we know. Now, let's get even stranger. Some cosmologists believe the universe could have emerged from a quantum fluctuation in this energy-rich vacuum. Essentially a tiny hiccup in a sea of probability. Imagine a balloon suddenly inflating out of nowhere, with space and time emerging along with it. That's one way of describing the Big Bang, not as an explosion in space, but as the expansion of space itself. A universe being written into existence, with its own geometry, energy, and, crucially, its own rules. And here's the truly fascinating part. Those rules may have existed before the universe did. Not as physical tablets etched into a cosmic stone, but as timeless truths, abstract structures that don't need space or time to exist. In this view, the laws of physics aren't just features of our universe. They're deeper, possibly eternal patterns that the universe had to follow once it began. Think of it like this. The number 3 exists, even if there are no apples to count. Similarly, the laws of logic, mathematics, and symmetry might exist independently of space and matter. They're not made of stuff. They're more like relations, pure structure. You don't need a room to have geometry. You need geometry to have a room. If that sounds philosophical, you're not alone. Many physicists tread carefully around this question, aware that they're brushing up against metaphysics. But it's an important issue nonetheless. If the laws of physics didn't come from the universe, then where did they come from? Were they always there, like a ghostly instruction manual waiting in the wings? Or did they emerge with the universe itself, evolving alongside the fabric of space-time? Some theories, particularly those influenced by quantum gravity and string theory, suggest that laws themselves might be emergent, arising from deeper, more fundamental rules. It's like opening a book and discovering not only the story but the language in which it's written is also forming in real time. Others argue that the laws are built into the very definition of a universe, that any universe, by definition, must follow some kind of consistent rules, otherwise it would collapse into incoherence or never exist at all. In this way, laws are the precondition for being. Without them, there's no framework for existence. No structure to build galaxies or guide evolution, no way to tell a photon from a pebble. We often think of laws as descriptions, not prescriptions. Gravity doesn't obey Newton's equations, it just does what it does, and we write equations to describe it. But when we reach this primal moment, the boundary between description and prescription gets fuzzy. If the universe was born with certain laws, and those laws are the only reason anything works at all, then they're not just descriptive, they're formative. They don't just say how things behave, they allow behaviour to exist. And intriguingly, our universe didn't just pop out with random rules, it came with a very specific, finely tuned set. If gravity were a bit stronger, stars might collapse too quickly. If it were weaker, they might never form. If the electromagnetic force behaved differently, atoms wouldn't bind. These aren't just mathematical curiosities. They're the scaffolding that makes structure possible. That makes us possible. This leads to the question of selection. Why this set of rules and not another? Some physicists propose a multiverse, an unimaginably vast ensemble of universes, each with its own laws. In such a landscape, we happen to live in one where the rules permit stars, chemistry, consciousness. Not because we're special, but because only in this kind of universe could something like us observe it. Of course, this is speculative territory. We can't yet test other universes, and might never be able to. But these ideas help us think more clearly about the strange situation we're in. A world built not from objects first, but from patterns, from logic, from relationships that don't take up space, but give space its meaning. And so, the idea of nothing slips away. The nothing before the universe may not have been the absence of everything, but the presence of pure possibility. A strange realm where rules hovered without time, waiting for a moment that would be the beginning of moments. In the end, the silence before the Big Bang might not have been empty. It might have been full of hidden structure, laws not yet woven into fabric but already capable of stitching space and time together. Quiet rules, waiting in the wings. The first whisper of something from what we thought was nothing. About 13.8 billion years ago, something extraordinary happened. In an instant, so fast it makes lightning look lazy, the universe burst into being. Not just matter, not just energy, but space itself, expanding outward from what we now call the Big Bang. And with that expansion came the very first whisper of rules. We tend to think of the Big Bang as a massive explosion, like the universe got overexcited and blew up in all directions. But that's a bit misleading. It wasn't an explosion in space, it was an expansion of space. There was no center, no outside, no background. Just space stretching from every point all at once, creating the canvas on which everything else would be painted. But even this canvas needed structure. Expansion alone doesn't explain stars or atoms or galaxies. It doesn't even explain what makes things behave the way they do. That part comes from the laws of physics. Those deep, quiet patterns that govern how energy moves, how particles interact, how forces pull and push and twist. What's fascinating is that these laws didn't just show up later, they were there from the very first moment. In fact, some physicists believe they were the reason the universe could begin at all. One idea is that laws like gravity, electromagnetism, and the strong and weak nuclear forces were baked into the universe as it was born. They weren't added later like toppings on a cosmic pizza. They were part of the dough, essential ingredients from the start. But were these laws fixed right away, or did they evolve over time? That's still an open question. Many physicists suspect that in the earliest fractions of a second, the universe was in a super-hot, supersymmetric state, where the forces we know today were unified into a single megaforce. Imagine gravity and electromagnetism, and the nuclear forces all mashed together, indistinct, like instruments playing a single note before splitting off into their own melodies. As the universe cooled, remarkably quickly mind you, this symmetry broke. The unified force split into separate pieces. Gravity went one way, the strong nuclear force another, and eventually electromagnetism and the weak nuclear force parted ways too. Each force took on its own identity, with its own range, strength, and role in the great cosmic ballet. This process is known as symmetry breaking. It's a bit like ice forming from water. The water is uniform and featureless, but when it freezes it develops a crystal structure. A pattern appears where before there was none. That's what happened with the forces. As the universe cooled, patterns crystallized out of the energetic fog, and with those patterns came rules. The laws of physics are astonishingly precise. For example, the strength of the gravitational constant is fixed to an absurd number of decimal places. If it were slightly different, just a smidge stronger or weaker, the universe as we know it wouldn't work. Stars might not form, galaxies might never pull together, chemistry might be impossible. This raises a compelling question. Did the universe choose its laws, or were they selected from a wider menu of possibilities? Some theories suggest there could be a vast multiverse out there, an endless landscape of universes, each with its own set of rules. In this view, we happen to live in a universe where the laws allow for complexity, because otherwise we wouldn't be here to wonder about them. It's not that our universe is special, it's that only in this kind of universe could observers like us emerge. Other ideas lean toward inevitability. Perhaps the laws had to be this way, not chosen, not random, but dictated by deeper principles we've only begun to glimpse. Some physicists are searching for a theory of everything, a single framework that unites all the forces and shows why they must be the way they are. String theory is one such candidate, although it's still more math than confirmed physics at this stage. Whether or not such a theory exists, one thing is clear. The early universe was an astonishingly tidy place. In its first trillionth of a second, it went through a burst of exponential inflation, expanding faster than the speed of light, not violating the cosmic speed limit, but stretching space itself. This inflation helped smooth out any wrinkles in the early cosmos, setting the stage for the uniform laws that followed. Inflation also amplified tiny quantum fluctuations, microscopic ripples in energy, into macroscopic differences in density. These little ripples became the seeds of all future structure. Stars, galaxies, you name it. Without them, the universe would be flat and featureless, perfectly smooth, and ironically perfectly uninhabitable. And yet, beneath all this action, the laws held steady. They provided the scaffolding for inflation, for symmetry breaking, for the cooling and clustering of matter. Without those laws, none of it would have made sense. The energy would have fizzled, the matter would have scattered, space would have remained silent and barren. Even time itself, the very idea of before and after, only becomes meaningful in a lawful universe. Without consistent rules, there's no reason for cause to lead to effect, no reason for heat to flow or motion to persist. The laws of physics don't just shape what happens, they define what it means for anything to happen at all. This brings us to a quiet but profound realization. Laws may not be things that happen within the universe. They may be the conditions for any universe to happen in the first place. In that sense, they're not part of the furniture of reality. They're more like the blueprint, or perhaps the rhythm. Because when you look closely, the universe behaves more like a melody than a machine. It unfolds in time, governed by ratios and symmetries and harmonies. Particles oscillate, fields vibrate, forces act in balance and counterbalance, and through it all the laws keep perfect time. They don't change their tempo, they don't improvise, they don't need to, they simply are, quietly present, invisibly guiding, infinitely reliable. And whether they emerged alongside the Big Bang or gave rise to it themselves, they have remained astonishingly consistent ever since. A cosmic script, written not in ink, but in relation. A quiet whisper at the birth of time still echoing through every atom today. The universe, for all its dazzling variety and cosmic drama, runs on a remarkably small set of rules. And even more curiously, those rules rely on numbers, specific, unchanging values known as physical constants. These numbers are the foundation beneath everything from gravity and light to atoms and stars. They're not just important, they're essential. Without them, nothing would behave the way it does. Or to put it less delicately, nothing would behave at all. Take the speed of a light, for example, about 299,792,458 meters per second. Not exactly a round number, but very much a reliable one. No matter where you are in the universe or how fast you're moving, light always zips along at that exact pace through the vacuum of space. No speeding, no slowing down for a coffee break. Just unwavering consistency. This might seem arbitrary at first. Why that number? Why not twice as fast? Or half? But if you tweak the speed of light even a little, everything else starts to unravel. A faster speed of light would change how quickly energy can move, which would affect how stars burn, how atoms hold together, and even how time flows. A slower speed would cramp the universe's style. Light wouldn't travel far, signals would crawl, and the cosmic microwave background might never have reached us. Now let's look at Planck's constant, the tiny number that governs the quantum world. It's roughly 6.626 times 10 to the minus 34 joule seconds. Yes, that's a decimal followed by 33 zeros and a 6. It's small, but mighty. Planck's constant is the bridge between the energy of a wave and its frequency. It's the reason why photons of blue light carry more energy than red ones, and why atoms can't just do whatever they want. Quantum behavior depends on this constant, like a dance follows a beat. Imagine turning the dial on Planck's constant just a bit. Suddenly, electrons might no longer stay confined to their cozy atomic orbits. Chemistry could become impossible. DNA wouldn't bind correctly, your tea wouldn't steep, cats might refuse to sit in boxes altogether. In short, reality would fall apart, possibly in spectacular, sparkly quantum fashion. And then there's the gravitational constant, often written as a capital G. It determines the strength of gravity, the glue that holds stars together and keeps planets in orbit. Gravity is incredibly weak compared to the other forces, which might be why the universe can afford to be so large. If G were even slightly stronger, stars would collapse under their own weight. If it were weaker, they might never ignite. The fact that we live in a universe where gravity is just the right strength to allow structure, but not too much of it, is one of those cosmic sweet spots that makes physicists raise their eyebrows and mutter, "interesting," in 10 different languages. These constants, light speed, Planck's constant, gravity's strength, and several others, form the backbone of what's sometimes called the standard model of physics. It's a tidy package of particles, forces, and relationships that explain almost everything we can observe. But the constants themselves are puzzling. They're measured with exquisite precision, but no one really knows why they have the values they do. They just are. like a recipe handed down without explanation, perfectly tuned but missing the backstory. If that sounds unsettling, don't worry, you're in good company. Many physicists have wrestled with this mystery. Some hope that future theories like string theory or quantum gravity might reveal deeper reasons for these values. Maybe they'll show that all the constants we observe are the result of some deeper mathematical necessity, inevitable, like the number pi popping up in circles. Others think it might be a cosmic coincidence, the result of chance among infinite possibilities. This is where the multiverse idea resurfaces, an enormous sea of potential universes, each with its own random set of constants. Most of these universes would be sterile or chaotic, but a tiny few would land on just the right values to make life possible. And we happen to live in one of those few, not because it was chosen, but because we couldn't be around to notice if it wasn't. Still others entertain the possibility that constants might not be constant at all. Over vast stretches of time or space, they could shift ever so slightly, just enough to make physicists very excited and philosophers slightly nervous. Some studies have hinted that the fine structure constant, which governs the strength of electromagnetic interactions, might have varied in distant parts of the universe. The evidence is still debated, but if it turns out to be true, it would mean the laws of physics aren't as fixed as we thought. They might evolve, or drift. It's a wild idea. Imagine building a house where the bricks slowly change size, the angles of the walls morph, and gravity rearranges itself. That's the level of unpredictability we'd be dealing with. And yet, here we are, living in a universe where the constants have remained stable enough for billions of years to allow stars to shine, molecules to form, and humans to ask very inconvenient questions about the nature of reality. And really, these constants are more than just numbers. They define the very scale of our universe. Planck's constant sets the size of quantum effects. The speed of light sets the pace of causality. The gravitational constant sets the structure of space. These values tell the universe how big to be, how fast things can move, and how strong the forces should be. They're like the dials on a cosmic mixing board, adjusted with such precision that even the tiniest nudge would change the song entirely. When physicists measure these constants, they do so with almost reverent care. Instruments are cooled to near absolute zero, isolated from vibrations and shielded from magnetic fields. Lasers bounce, particles dance, and equations whisper their secrets, all to coax out the tiniest digits of precision. The better we understand these constants, the better we understand the universe. But still, questions remain. Are these numbers truly fundamental, or are they hints of something deeper? Could they be derived from a more elegant framework we've yet to discover? Or are they just cosmic quirks, like the universe's favourite lottery numbers? No one knows for sure. But what we do know is that without these constants, nothing would be the same. There would be no galaxies, no chemistry, no atoms, and most certainly no quiet videos about physics to lull you to sleep. In their silence, these constants do more than just keep the universe running. They create a kind of harmony, a deep structural rhythm that everything else must follow. From photons racing across galaxies to electrons spinning in the atoms of your pillow, all of it dances to the same cosmic beat. And yet, as perfectly tuned as it all seems, we're still not sure whether the melody is composed, discovered, or simply played. There's a number quietly tucked into the fabric of reality that seems almost too strange to be real. It doesn't have units. It doesn't refer to a particular thing. It's just a pure, dimensionless ratio, about 1 divided by 137, that shows up again and again in the laws of physics. It's called the fine structure constant, and it might just be one of the most mysterious numbers in the universe. Unlike other constants, the fine structure constant doesn't measure a speed or a force or an energy. Instead, it tells us how strongly charged particles like electrons interact with electromagnetic fields. In simpler terms, it governs how light and matter talk to each other. It's the quiet mediator behind everything from how atoms hold together to how stars shine. Its value is approximately 0.007297, or more commonly 1 divided by 137.035999, and so on. Not exactly a number you'd play in a lottery, but it has a certain poetic flair. Physicist Richard Feynman once called it one of the greatest damn mysteries of physics, and suggested that every physicist should have it hanging on their wall with a note that says, "You explain this." What makes this number so strange is that it doesn't come from anywhere obvious. It isn't derived from other constants. It doesn't emerge neatly from equations. It's just there. A quiet whisper in the background of every interaction between light and charged particles. We measure it with exquisite care, but no one can quite say why it has the value it does. If it were even a little bit different, the consequences would ripple across the entire universe. If the fine structure constant was slightly larger, electrons would orbit nuclei more tightly. Chemical bonds would be stronger. Atoms might not behave the way they do, and complex chemistry, the kind that gives rise to life, could become impossible. On the other hand, if the constant was smaller, electrons might drift too loosely. Atoms would struggle to hold together, and stable matter might never form in the first place. Stars might burn too quickly or never ignite at all. The delicate balance that allows complexity would tip into chaos. This makes the fine structure constant one of the cornerstones of what physicists call the anthropic principle. The idea is that we observe certain physical constants to have life-permitting values, because if they didn't, we wouldn't be here to observe them. It sounds a bit circular, and it is, but it raises an interesting point. There may be no deep reason why the fine structure constant has the value it does. It could just be one of those cosmic quirks that happens to be just right. Still, many physicists aren't satisfied with that answer. They'd like to believe there's something deeper, something that explains why this number is what it is. Could it be related to the geometry of spacetime, to hidden dimensions, to some undiscovered symmetry that unites all the forces of nature? One of the things that sets the fine structure constant apart is that it's dimensionless. Most constants in physics, like the speed of light or Newton's gravitational constant, depend on the units we use. But the fine structure constant doesn't care whether you measure distance in meters or miles, time in seconds or centuries. It's a pure number. That makes it a kind of universal fingerprint, something that could be recognized by any intelligent beings anywhere in the universe, no matter how they measure things. This has led some to speculate that the fine structure constant might be the kind of thing you'd send in a message to aliens. Forget language or pictures, just send them 1 divided by 137. If they know physics, they'll know what it means. It would be like saying, we know about light, we know about atoms, we know about you in a way. The name fine structure constant comes from its role in explaining the tiny splitting seen in the spectra of atoms. When light is emitted by excited electrons dropping to lower energy levels, it doesn't always come out as one clean line. Instead, you see closely spaced lines. Fine structure. This splitting is caused by relativistic effects and the interaction between the electron's spin and its motion around the nucleus. And it just so happens that the size of that splitting is governed by this constant. But its influence doesn't stop there. It pops up in quantum electrodynamics, the theory that describes how light and matter interact. It shows up in the behavior of particles and accelerators. It even plays a role in the way fundamental forces behave at different energy levels. In a way, it's everywhere, and yet we can't pin down where it came from. Some researchers have explored whether the fine structure constant might vary over time or space. After all, if it's just a number with no known origin, who's to say it must stay the same forever? Observations of distant galaxies have been used to test this idea, because looking far away is like looking back in time. If the constant were different billions of years ago, we might see subtle shifts in the light from ancient quasars. So far, the results are mixed. Some studies have hinted at tiny variations, others have found nothing. The jury is still out, but if such a variation were ever confirmed, It would shake the foundations of modern physics. It would mean that what we think of as fixed and fundamental is in fact dynamic and evolving. There are also more speculative ideas. Some have suggested that the fine structure constant might be related to the mathematical constants, pi or e, or perhaps to some as yet undiscovered feature of the universe's topology. Others have wondered if it could emerge from a deeper theory of everything, a framework in which all the constants are connected and one value leads inevitably to another. But so far, no theory has pulled the pieces together in a way that explains this particular number. It's tempting to think of the fine structure constant as a kind of cosmic signature, not a message from anyone, but a subtle hint from the universe itself, saying, this is how the rules are written. In a world of particles and forces, it's a point of stillness, a number that doesn't change, doesn't move, but allows everything else to happen. When you flip on a light switch, the glow that fills the room is shaped by this constant. When atoms bond to form molecules, when stars fuse hydrogen into helium, when your eyes take in colour, all of it depends on that little number. It's the thread woven through the tapestry of reality, too small to notice, too essential to ignore. And the strangest part is, we don't know whether it's a clue or just a fact, a placeholder for a deeper answer, or the answer itself. Maybe one day we'll understand why it's 1 divided by 137 and not something else. Or maybe we'll just keep measuring it, marvelling at it, and watching the universe dance obediently to its tune. If you strip reality down to its barest bones, past atoms, past particles, past even the curious buzz of quantum fields, you begin to see something remarkable. Patterns, ratios, symmetries, relationships so consistent and elegant they look suspiciously like mathematics. It's almost as if the universe isn't built from matter at all, but from math itself. Not static math, though. This is math in motion. A graceful unfolding of numbers through time and space, like a dance choreographed by logic. The idea that the universe runs on math isn't just poetic, it's astonishingly effective. Every law of physics, from the path of a falling apple to the orbit of a distant galaxy, can be described with equations. Not vague approximations, but precise formulations. Newton's second law of motion, force equals mass times acceleration. Maxwell's equations for electromagnetism, Einstein's famous E equals mc squared. These aren't just scribbles on a chalkboard. They describe how the universe behaves, how it must behave. When Isaac Newton first formulated his laws of motion in the 17th century, he wasn't just describing falling objects, he was writing the language of the cosmos. With a handful of equations, he could predict how planets moved, how tides rose, how cannonballs flew. The beauty of it was in the simplicity. Nature was complex, but its rules were clean. And this cleanliness, this order, hinted at something deeper. That the universe obeys rules not because it chooses to, but because it is the rule. Everything we observe is an expression of those rules in action, math set into motion. Centuries later, Albert Einstein would take this idea even further. His general theory of relativity, published in 1915, reimagined gravity not as a force, but as geometry. Massive objects like stars and planets bend spacetime around them, and other objects follow those curves. The equations that describe this, Einstein's field equations, aren't just powerful, they're beautiful. They unite matter, energy and geometry into a single, elegant framework. What's astonishing is that Einstein's theory predicted things long before we could observe them. Gravitational waves, for example, ripples in the fabric of space-time, were predicted a century before we had instruments sensitive enough to detect them. When LIGO finally confirmed their existence in 2015, it was like hearing the music of the universe echoing exactly in tune with the sheet music we'd written. This ability of mathematics to not just describe reality, but predict it, is what makes it feel so fundamental. When physicists write down equations, they're not inventing the laws, they're uncovering them. It's less like creating art and more like discovering fossils in the ground. The patterns were always there. We're just brushing away the dust. But here's the curious part. Why should the universe be mathematical at all? There's no obvious reason why reality should obey equations. Why not something messier, more chaotic, less consistent? And yet, from the spacing of planetary orbits to the harmonics of vibrating strings, the universe seems to prefer order. Even chaos, when you look closely, has structure. The weather is unpredictable day to day, but follows long-term patterns governed by the Navier-Stokes equations. The stock market fluctuates wildly, but statistical physics can still be used to model its trends. In nature, even the randomness obeys rules. Some physicists and mathematicians argue that this deep link between math and the universe suggests that mathematics is not just a language we use to describe nature, but something nature is. That the fabric of reality is mathematical in its essence. This idea isn't new. Philosophers as far back as Pythagoras believed that numbers were at the heart of all things. Galileo once said that the universe is written in the language of mathematics, and that without understanding its symbols we cannot comprehend it. It's not hard to see why. From the spiral of a galaxy to the symmetry of a snowflake, math is everywhere. And it gets even more mind-bending when you enter the quantum realm. At the smallest scales, particles don't behave like little billiard balls. They behave like waves, probabilities, patterns of interference. The equations that govern this, like Schrödinger's wave equation, don't describe where a particle is, but where it might be. Reality at that scale is not definite until it's observed. And yet, even this uncertainty is ruled by precise mathematics. The weirdest part? These equations are stunningly accurate. Quantum electrodynamics, for instance, is the most precisely tested theory in the history of science. Predictions made using its math agree with experiments to within 1 part in a billion. That's like predicting the width of the United States to the accuracy of a single human hair. All from math. Of course, not every part of physics is solved. The quantum world and the relativistic world still don't play nicely together. Efforts to unify them, like string theory, are filled with rich mathematics, but so far lack experimental confirmation. And yet, even in these theories, math guides the way. It suggests possible shapes of extra dimensions, patterns of vibration that might give rise to particles, symmetries that could explain why forces behave as they do. Math, in this sense, is both map and compass. It shows us where we are and hints at where we might go next. But perhaps the most poetic example of math in motion comes from something much closer to home. Music. Notes vibrating at different frequencies, combining into harmonies. Patterns repeating, but never quite the same. Music is math experienced emotionally, numbers made audible. In a way, the universe is doing something similar. It hums, it resonates, it unfolds. And like music, it has rules. You can't just play any notes in any order and expect it to sound pleasant. There's structure, rhythm, intervals. In physics, these show up as conservation laws, symmetries and equations. In music, they're chords and time signatures. But the logic is oddly similar. Even the way matter forms reflects this musicality. Electrons orbit atomic nuclei in discrete energy levels, like notes in a scale. Transitions between levels release photons, particles of light, with specific frequencies. That's why each element glows a particular color when heated. You're seeing atoms play their tune. In the end, the universe might be best described not as a machine, but as a kind of unfolding algorithm, an infinite expression of mathematical principles dancing through time. And the most beautiful part is this. We, as thinking beings, are part of that dance. Our brains are wired to recognize patterns, to seek order, to make sense of equations. We are math, studying math. Conscious stardust doing long division. Whether or not we ever find the final formula, the grand equation that unites every force and every particle, there's something quietly comforting in the idea that the universe follows rules. That, behind the storms and stars and subatomic strangeness, there is structure, there is symmetry, there is sense. Even if it's a kind of sense that whispers rather than shouts, one that flows rather than stands still, a logic not carved in stone, but written in motion. There's something quietly astonishing about waking up in the same universe every day, one where gravity still pulls down instead of up, where atoms don't suddenly fly apart in protest, and where light, no matter what, always travels at the same speed. It's easy to take this for granted, but it's actually quite extraordinary. The universe is incredibly well behaved. In a place so vast and ancient, you'd think the rules might slip occasionally. But no, the cosmos runs like a clock that's never once lost a second. At the heart of this consistency are the laws of physics. But what makes them so reliable? Why don't particles take a day off? Why is nature so disciplined? One reason is that the laws of physics aren't suggestions. They're built-in properties of the universe. They aren't enforced by any authority. There's no cosmic referee blowing a whistle when an atom tries to misbehave. Instead, the rules are embedded in the very structure of reality. Things don't obey them because they're being watched. They obey them because they couldn't do otherwise. Take light, for example. No matter where you are or how fast you're moving, light in a vacuum always zips along at just under 300 million meters per second. That's not a speed limit with speeding tickets. It's simply the speed that light is. It's not trying to hit that number. It's not varying slightly on off days. That's just its nature. This exactness isn't just a quirky feature of light. It runs deep through all of physics. Particles have precise masses. Forces have exact strengths. Constants like the gravitational constant and Planck's constant never seem to flinch. The electron, one of the most well-studied particles in the universe, has the same mass and charge everywhere it's been measured, from labs on Earth to the outer reaches of space. Even more curious is how reliably things interact. Electrons repel each other with a specific strength. Quarks bind together to form protons and neutrons with perfect consistency. When a star fuses hydrogen into helium, it releases the same predictable amount of energy every time. There are no accidents, no off-brand atoms that behave slightly differently on Wednesdays. This regularity gives rise to everything we call stable: matter, chemistry, stars, planets, people. Without consistent rules, atoms wouldn't form, molecules wouldn't stay bonded, DNA wouldn't replicate. The idea of cause and effect would collapse. You might drink water one day and sulfuric acid the next, and good luck brushing your teeth after that. One of the big ideas that helps explain this cosmic order is called symmetry. In physics, symmetry doesn't just mean something looks the same. It means something behaves the same under certain changes. For example, if you do an experiment today and repeat it tomorrow in the same way, and you get the same result, then the laws are symmetric in time. If you rotate your lab 90 degrees and the physics doesn't change, that's symmetry in space. These symmetries are connected to conservation laws, beautiful links between what stays the same and what can never be created or destroyed. Thanks to a mathematical result known as Noether's theorem, we know that every symmetry corresponds to a conserved quantity. Symmetry in time, that gives us conservation of energy. Symmetry in space, conservation of momentum. This elegant framework is one of the reasons physics works so well. It explains not only that the universe is lawful, but why the laws take the forms they do. But still, it's tempting to wonder, why does the universe have any laws at all? Why not a world where things shift unpredictably, where electrons sometimes wander off their tracks, where gravity forgets to show up? Some physicists argue that we could only find ourselves in a lawful universe because only such a place could produce observers. In a chaotic universe with no stable structures, no one would be around to notice. It's a bit of an existential game of hide and seek. Only universes that allow for consciousness will have anyone wondering why they allow for consciousness. This is part of what's called the anthropic principle. It doesn't explain why our universe is lawful exactly. It just points out that if it weren't, we wouldn't be here to ask the question. That might sound like a philosophical shrug, but it does underscore how rare and precious our kind of universe might be. Others believe the order we see is the result of something deeper. Perhaps the laws aren't arbitrary, but necessary. That once you allow for any kind of existence at all, the laws follow inevitably. They're the logical scaffolding that makes existence possible. A sort of cosmic grammar that emerges as soon as anything exists to follow it. Or maybe the laws themselves are emergent. Some theories suggest that what we call laws of physics arise from even more fundamental processes. Just as temperature emerges from the chaotic motion of molecules, the stability of particles and forces might arise from deeper statistical or quantum rules. In that view, the order we observe is like the surface of a calm lake, serene, but underpinned by frantic motion below. It's also possible that the universe is lawful because chaos simply doesn't scale well. You can have small, random fluctuations, quantum blips, thermal noise, but to build something big and stable, you need patterns. Without consistency, you can't get stars or planets or life. So the universe, in evolving toward complexity, naturally favours order. Whatever the reason, we benefit from this predictability in every moment. Your phone works because electrons behave reliably. Your heartbeat keeps time because ions flow consistently across cell membranes. The tides roll in because the moon follows Newton's laws with unrelenting discipline. In fact, every piece of technology, every measurement, every scientific experiment is a quiet vote of confidence in the idea that the universe will behave tomorrow the same way it did today. And so far, it always has. Even randomness in physics isn't truly lawless. At the quantum level, particles behave probabilistically. You can't say exactly where an electron is, only where it's likely to be. But even that randomness follows rules. The probabilities are exact. The uncertainty is predictable. It's not chaos. It's a different kind of order. One that feels strange to us, but still marches to a steady beat. It's worth noting that this regularity gives science its power. We can build models, we can make predictions, we can test hypotheses. None of that would work in a universe where the rules kept changing. Without lawful behaviour, knowledge itself would unravel. Every fact would have an expiration date. And yet, despite how reliable the universe is, there's still room for wonder. The laws may be fixed, but their consequences are endlessly varied. From the swirl of a hurricane to the lattice of a snowflake, from the spiral arms of a galaxy to the heartbeat of a newborn child. All of it built on the same quiet rules. Maybe that's the most surprising thing of all. That out of a handful of constants, a few symmetrical relationships, and some deeply stable patterns, the universe can generate such astonishing richness. It doesn't need chaos to be interesting, it just needs rules consistently followed, and it's been following them, quite dutifully for over 13 billion years. Imagine you're handed the control panel to the universe. Buttons and dials for gravity, electromagnetism, the strong and weak nuclear forces, even the speed of light. No password required, just you and the fundamental constants of nature. The temptation to tweak a few settings might be irresistible. Maybe you want a universe where gravity is a little stronger, or where light travels just a bit faster, but be warned, even the tiniest nudge might unravel everything. It turns out our universe is remarkably sensitive to its own rules. Like a complex machine held together by invisible threads, everything from the formation of atoms to the evolution of life depends on the precise tuning of certain constants. Adjust one dial slightly, and the universe could end up lifeless, chaotic, or very, very boring. Take gravity. It might feel strong when you're lugging groceries up the stairs, but on a cosmic scale, gravity is absurdly weak. About 39 orders of magnitude weaker than the electromagnetic force. That's a 1 followed by 39 zeros. And yet, it's just strong enough to hold galaxies together, form stars and keep planets in orbit. If gravity were even slightly stronger, stars would burn through their fuel too quickly. They'd be short-lived, unstable, and probably incapable of producing the heavier elements needed for life. Make gravity slightly weaker, and stars might never ignite at all. Matter would drift apart, too diffuse to coalesce. The night sky might be forever dark. Now turn your attention to the strong nuclear force, the force that binds protons and neutrons in the atomic nucleus. It's incredibly powerful, but only over very short distances. If it were just a tiny bit weaker, protons wouldn't stick together and hydrogen would be the only element in existence. No carbon, no oxygen, no chemistry beyond the very simplest. On the flip side, if the strong force were just a bit stronger, nuclear fusion might be so efficient that all hydrogen would burn up too quickly, leaving no fuel for long-lived stars or water as we know it. Even the mass of the electron plays a pivotal role. If electrons were much heavier, atoms would be smaller and denser, changing the structure of matter entirely. If they were much lighter, atoms might not be able to form at all. Electrons need just the right mass to orbit nuclei in stable configurations, balancing the pull of the nucleus with the rules of quantum mechanics. It's a cosmic Goldilocks situation. Too heavy, too light, and nothing works. The same goes for the ratio of the electromagnetic force to gravity. This ratio determines the structure of stars and planets. If electromagnetic interactions were much weaker compared to gravity, stars would be enormous, short-lived and inhospitable. If they were much stronger, matter would be too tightly bound and fusion might never begin. You wouldn't just lose stars, you'd lose the possibility of any energy exchange complex enough to support life. The fine structure constant makes another appearance here. This little number governs how strongly particles interact with electromagnetic fields. As we've seen, if it were slightly different, atoms wouldn't form the same way. Chemistry would change, and the spectrum of light itself might shift in ways that make photosynthesis, or even vision, impossible. Even the dimensionality of space matters. We live in a universe with 3 spatial dimensions and 1 time dimension, and that turns out to be incredibly convenient. If space had 2 dimensions, gravity would behave differently and orbits wouldn't be stable. Planets would either spiral into their stars or drift away forever. With 4 or more spatial dimensions, forces would dilute too quickly with distance, and stable atoms might not be possible. Life, at least as we know it, would never get a foothold. Time is another interesting dial. We experience time as a single, forward-moving dimension. It flows one way, thanks largely to entropy. But what if time had more dimensions, or none at all? Multiple dimensions of time would make causality, a clear sequence of events, nearly impossible. You might have effects without causes, or causes without any effect. Planning your calendar would become an existential nightmare. Even more curious is the cosmological constant, a value that determines how fast the universe expands. If it were just a bit larger, space would stretch so rapidly that galaxies could never form. Too small, and the universe might collapse back in on itself before anything interesting could happen. Current estimates suggest that the value of the cosmological constant is finely tuned to allow cosmic structure to develop over billions of years. Physicists sometimes refer to this delicately balanced situation as fine-tuning. It's as if the universe were set up to allow for complexity, structure, and, eventually, life. This doesn't necessarily mean it was designed that way. It could be that only in a universe where the tuning is just right can observers exist to notice it. That's the anthropic principle again. Perhaps not entirely satisfying, but difficult to argue with. There are also alternative theories that sidestep the fine-tuning issue. One idea is that we live in a multiverse, a vast ensemble of universes, each with different constants and laws. Most of these universes would be sterile or wildly unstable. Ours is simply one of the rare ones where things clicked into place just right. It's a bit like winning the cosmic lottery, except no one remembers buying a ticket. Other theories suggest that the laws we observe may not be fundamental at all. They could be emergent, arising from deeper principles we don't yet understand. Like the shape of a snowflake coming from the motion of a water molecules, the laws of physics might be surface patterns on a deeper, stranger reality. And yet, even with all the speculation, we can't ignore how razor-thin the margins seem to be. Shift a few decimal points, and the whole show collapses. No stars, no planets, no chemistry, no life. Just a silent, lifeless void, or worse, a universe that flashes into existence and disappears before it can do anything interesting. At the same time, it's important not to fall into the trap of thinking the universe is designed for us. In reality, we're shaped by the universe, not the other way around. Our bodies, our biology, even our thoughts are finely tuned to this particular set of rules because this is the environment that allowed us to evolve. If the rules were different, perhaps some other form of complexity would arise, something beyond our imagination. Or maybe not. Maybe we live in one of the very few universes where the rules allow anything at all to happen. So what if the rules were different? Then the universe would be different. Or perhaps there would be no universe at all. It's a thought experiment that invites awe, not fear. Because the real miracle isn't that things are the way they are. It's that somehow the rules clicked into place to allow anything at all to be. And in this delicate balance of constants and forces, here we are, able to ask questions, ponder possibilities, and gently marvel at how just right it all seems to be. Symmetry is one of those quiet forces in the universe that seems almost too elegant to be real. We often think of symmetry as something visual, a butterfly's wings, a snowflake's arms, the mirrored halves of a face. But in physics, symmetry runs much deeper than appearances. It's not just about beauty, it's about balance, consistency, and the very structure of the laws that govern everything. At its heart, symmetry is about transformations. If you perform some action, say, rotate a system, or shift it slightly in space, or time, and the laws of physics still apply in exactly the same way, that's symmetry. And this isn't just a convenient property, it's a deeply powerful one. It turns out that the symmetries of the universe are tightly linked to the things that never change, the stuff we call conservation laws. This connection was formally uncovered by a brilliant mathematician named Emmy Noether in the early 20th century. Her theorem, appropriately called Noether's theorem, is one of the most elegant and important results in theoretical physics. It tells us that every continuous symmetry in nature corresponds to a conserved quantity. For example, if the laws of physics are the same today as they were yesterday, then energy must be conserved. That's symmetry in time. If the laws don't care where in space you are, on the moon or in your kitchen, then momentum is conserved. That's symmetry in space. If the laws behave the same no matter which direction you face, then angular momentum is conserved. So if you're spinning in a swivel chair and pull your arms in, you spin faster. That's not just a party trick, it's physics showing off its commitment to symmetry. These symmetries aren't just mathematical curiosities. They're the reason you can launch a satellite, design a roller coaster, or pour tea without it spontaneously flying sideways. They are why particles behave consistently, why orbits are stable, and why you don't have to recalibrate your entire understanding of reality every Tuesday. But symmetry's role in physics goes even deeper than that. The fundamental forces themselves, gravity, electromagnetism, the strong and weak nuclear forces, are all rooted in symmetry principles. In fact, physicists have found that you can derive entire interactions by demanding that certain symmetries must be preserved. Take electromagnetism. It comes from a symmetry called U1, which essentially means that the equations don't change when you shift the phase of a wave function. That might sound abstract, and, well, it is, but this little mathematical quirk is the very reason light exists. It's the reason your phone connects to Wi-Fi, your microwave heats food, and stars shine in the sky. All because of a hidden symmetry that insists on sticking around. The strong nuclear force, which holds atomic nuclei together, is based on a more complicated symmetry called SU3, and the weak nuclear force, which plays a key role in radioactive decay, comes from SU2. These names sound like robot models from a sci-fi movie, but they describe very specific kinds of mathematical symmetries. Entire fields of particles and their interactions emerge simply because nature seems to respect these abstract transformations. And then there's gravity. Einstein's general relativity is built on the idea of local symmetry in spacetime itself. The laws of physics look the same no matter how you bend or stretch your coordinates, as long as you do it smoothly. This is why gravity is described as the curvature of spacetime, rather than a force pulling things toward one another. It's a reflection of the deep symmetry woven into the geometry of the cosmos. But nature isn't perfectly symmetric all the time, and that's where things get really interesting. Sometimes the laws have a symmetry, but the solutions to those laws break it. This is called spontaneous symmetry breaking. Imagine a round table with a ball balanced perfectly on top. The ball could fall in any direction, and the table doesn't favour one over another. That's symmetry. But the moment the ball falls, it picks a direction. The symmetry is broken, not in the laws, but in the outcome. This kind of symmetry breaking is what allows particles to have mass. In the early universe, the electroweak force was unified. Electromagnetism and the weak force were one and the same. But as the universe cooled, this symmetry broke, and the Higgs field gave mass to some particles while leaving others, like the photon, massless. The result? A world where particles move at different speeds, interact differently, and form the rich tapestry of matter we know today. Without symmetry breaking, the universe would be a very dull place, possibly an empty one. Symmetry may be the foundation, but it's the breaking of symmetry that gives rise to diversity, structure, and complexity. Snowflakes form when water molecules break rotational symmetry. Crystals grow when atoms settle into repeating patterns, breaking translational symmetry. Even the left-right imbalance in biological molecules, a preference for left-handed amino acids, for instance, is a form of broken symmetry that's vital to life. Sometimes the universe breaks symmetry in subtle ways, like in the case of matter and antimatter. For every particle, there's an antiparticle with the opposite charge. You'd expect the Big Bang to have created equal amounts of both, but it didn't. Something tipped the scales just slightly in favour of matter, and now here we are. That tiny asymmetry, buried deep in the laws of particle physics, is the reason you're not made of nothing at all. Even time, which feels like a steady march from past to future, involves symmetry, or rather the breaking of it. Most of the fundamental laws of physics work perfectly well if you run them backwards. They're time symmetric, but in the real world you never see a cup of spilled tea leap back onto the table. That's because of entropy, the tendency for systems to move from order to disorder. The laws may be time symmetric, but the universe chooses a direction. Once again, symmetry gives us the framework, but breaking it gives us the story. There's something comforting in knowing that the universe runs on symmetry. It's a kind of cosmic fairness. The rules don't change from one moment to the next or from one corner of space to another. There's no favoritism, no bias, just quiet, mathematical consistency. But the real beauty lies in how the universe mixes symmetry with just the right amount of imperfection, enough structure to build galaxies and enough asymmetry to make them spin, enough consistency to allow for life, and enough unpredictability to make it interesting. And perhaps that's the trick. The universe's favourite trick, really. Using symmetry not as a cage, but as a foundation. A way to create infinite variation from simple principles. Like a jazz musician riffing on a theme, reality plays with symmetry, sometimes honouring it, sometimes bending it, but always following the beat. In every orbit, every crystal, every photon, symmetry is quietly at work. And in every star, every snowflake, every thought, we see the subtle ways it gives way to something just slightly more interesting. A universe of balance and asymmetry, dancing in perfect imperfect harmony. If the universe had a rulebook, there would be a big, bold line somewhere near the front that reads, "Nothing goes faster than light." It's one of the most famous constraints in physics, and also one of the most misunderstood. Light speed isn't just fast, it's fundamental. It's not a suggestion, or a best-case scenario. It's a hard limit, a cosmic speed cap that shapes everything from how stars shine to how time flows. First, let's appreciate just how quick light really is. In the vacuum of space, light travels at approximately 299,792,458 meters per second. That's fast enough to circle the Earth more than 7 times in a single second. Sunlight takes just over 8 minutes to reach our planet, despite the fact that the Sun is about 93 million miles away. It's the Usain Bolt of the cosmos, and nothing, even in principle, can outrun it. But why is this speed so important? Why does it matter that light has a maximum velocity, and why can't anything exceed it? The answer lies in the fabric of spacetime itself. In the early 20th century, Albert Einstein revolutionized our understanding of space and time with his theory of special relativity. One of its core ideas is that the speed of light is the same for all observers, no matter how fast they're moving. Whether you're standing still or zipping along in a rocket, if you measure the speed of a beam of light, you'll always get the same number. This might not sound like a big deal, but it has mind-bending consequences. To make the speed of light constant for everyone, the universe has to adjust how time and space behave. If you move faster, time slows down for you relative to someone who's standing still. Your lengths contract. Simultaneity, what it means for two things to happen at the same time, becomes fuzzy. It's as if the universe is bending itself to protect the sanctity of that one speed. That speed limit also protects causality, the idea that cause comes before effect. If information could travel faster than light, it could, in some reference frames, arrive before it was sent. You could theoretically receive a message from yourself before you'd written it. Eggs could unscramble. Grandparents could be accidentally unexisted. The logical order of the universe would fall apart. Thankfully, the speed of light acts like a universal referee, making sure events follow a sensible order. If something happens here and now, it can't immediately affect something a billion light-years away. It takes time for influence to travel, and that delay is what gives the universe structure. It's why galaxies look the way they do, why the night sky is a glimpse into the past, and why watching a supernova is like seeing a celestial postcard arrive long after it was sent. Now, it's worth noting that when we say nothing goes faster than light, we mean no information or matter can travel faster than light in a vacuum. Light itself can slow down when it moves through a medium, like glass or water, but that's not breaking the rule, it's more like traffic congestion. The limit still applies to the raw maximum speed in empty space, and particles with mass can never quite reach light speed. The closer they get, the more energy it takes to keep accelerating. That energy requirement skyrockets the nearer you get to the limit, until it becomes effectively infinite. It's like trying to push a boulder up a hill that gets steeper and steeper with no summit in sight. No matter how hard you try, the laws of physics always push back. Photons, the particles of light, get around this by having no mass at all. They're the only things allowed to travel at exactly the speed limit, but that privilege comes at a price. They experience no passage of time. From a photon's perspective, if such a perspective could exist, the moment it's emitted and the moment it's absorbed are the same instant. It's a strange, almost timeless existence. Light doesn't just move fast, it glides across the universe in a kind of frozen eternity. The speed of light also ties directly into Einstein's most famous equation, E equals mc squared. This shows that mass and energy are interchangeable, with the speed of light squared acting as the conversion factor. It's not just a handy bit of math, it's a statement about the deep relationship between matter, energy, and the geometry of space-time. That little c isn't just about how fast photons travel, it's baked into the very fabric of reality. Curiously, the speed of light also sets a kind of horizon for what we can see. Because the universe is only so old, about 13.8 billion years, and light takes time to travel, there's a limit to how far we can observe. This isn't because there's a wall out there, but because the light from more distant regions simply hasn't had time to reach us yet. The observable universe is like a growing bubble, with light slowly filling in the picture. And yet, because space itself is expanding, there are parts of the universe that are already beyond our reach. Some galaxies are receding from us faster than light, not because they're moving through space at that speed, but because the space between us and them is stretching. In this case, the speed limit isn't technically being broken. It's more like the rug is being pulled out from under everything, and we're all sliding away from one another. These subtleties make the cosmic speed limit more than just a number. It's a boundary, a guide, a rule that defines how everything connects. It shapes how long it takes for starlight to reach us. It dictates the size and age of the universe. It even sets the pace at which we can dream of exploring the cosmos. Want to visit the nearest star system, Proxima Centauri? It's over 4 light-years away. Even if you could travel at 99% of the speed of light, it would still take years to get there, and the fuel bill would be problematic, to say the least. Despite its limitations, the speed of light also gives us clarity. It means the universe isn't chaotic or instantly connected in every direction. It forces interactions to happen within boundaries at paces that can be understood and predicted. It means we live in a cosmos that unfolds rather than snaps into being all at once. In a way, the speed of light is like the tempo of the universe. It keeps time. It defines rhythm. It sets the maximum pace for information, influence, and motion. It gives the cosmos a sense of order, a kind of structure that allows for causality, history, and meaning. So while we often think of speed as thrilling or flashy, the true value of light speed is in its restraint, its unwavering steadiness, its calm refusal to bend to impatience. It doesn't rush. It doesn't waver. It simply marks the edge of what's possible, and in doing so defines what it means to be real. Entropy has a bit of a reputation. It's often blamed for everything from the mess in your room to the eventual heat death of the universe. It's portrayed as a sort of cosmic villain, always increasing, always causing disorder, always turning the lights off on existence. But entropy isn't evil. In fact, without it, the universe wouldn't work at all. You wouldn't move. You wouldn't think. You wouldn't even exist. Entropy isn't just a law about disorder. It's the law that makes anything happen in the first place. Let's start with the basics. Entropy is a measure of disorder, or more precisely the number of microscopic ways a system can be arranged while still looking the same on a larger scale. Think of it like shuffling a deck of cards. If you open a fresh pack, the cards are in perfect order. There's only one way to have that exact arrangement. But once you start shuffling, the number of possible combinations explodes. Most of them will look random. That randomness, that vast increase in possible arrangements, is entropy. In thermodynamics, entropy is part of the second law. In a closed system, entropy never decreases. It either stays the same or increases. This is why heat always flows from hot objects to cold ones, never the other way around. If you put an ice cube into a cup of tea, the tea warms the ice, and the ice cools the tea. But you'll never see the ice get colder while the tea gets hotter, no matter how badly you might want to chill your drink faster. This might sound like a boring inevitability, but it's actually the engine of everything dynamic in the universe. Without increasing entropy, there would be no reason for energy to move. No currents, no winds, no stars burning, no water falling, no processes at all. Entropy is the driver of time's arrow, the reason we remember yesterday and not tomorrow. The fundamental equations of physics work perfectly well in reverse, but entropy gives them direction. It turns reversible math into irreversible experience. Imagine a sand castle. You build it carefully, grain by grain. The structure you've made is highly ordered, with only a few ways to arrange the grains and still call it a castle. But over time, the wind and waves wear it down. The grains spread out, flattening into the beach. The number of possible arrangements increases enormously, and so does the entropy. No law prevents the castle from spontaneously reassembling itself, but the odds of that happening are so mind-bogglingly low that you're more likely to win the lottery while being struck by lightning during a solar eclipse. That's entropy in action. Not a force, not a thing, but a measure of likelihood. High entropy means more possible microstates, more ways the particles can be arranged without us noticing the difference. Low entropy is rare and fragile, like a tidy bookshelf or a snowflake. This isn't just about sandcastles and tea. Entropy drives the universe at every scale. Stars form and shine because gas clouds collapse under gravity, converting gravitational potential into heat and light, processes that increase entropy. Planets cool, tectonic plates shift, volcanoes erupt, and all of it follows the path of increasing entropy. Even life, strange as it may sound, plays by entropy's rules. Your body's not a closed system. You eat food, breathe air, and release waste. Inside, you're creating order, building complex molecules and maintaining temperature gradients. But in doing so, you're increasing entropy in your surroundings. You take in low entropy food and oxygen and release high entropy heat and carbon dioxide. Life thrives by exporting disorder. Without entropy, evolution wouldn't have a direction, metabolism wouldn't happen, thinking wouldn't require energy. There would be no difference between an alive brain and a cold rock. Entropy also makes time feel real. If everything happened in perfectly reversible loops, if you could rewind your day like a video, there would be no clear past or future. But because entropy increases, we experience a consistent flow from before to after. Eggs break, but don't unbreak. Ink disperses in water, but doesn't gather back into drops. You age, but you don't de-age. Entropy is the universe's way of writing history, and it gives rise to one of the strangest puzzles in cosmology. Why was the universe so low in entropy at the beginning? The early universe, right after the Big Bang, was hot and dense and uniform. That might sound chaotic, but in thermodynamic terms, it was extremely ordered. Gravity hadn't yet pulled matter into stars or galaxies, so the energy was evenly distributed. That's a low entropy state. Over time, the universe expanded and cooled, and structures formed: galaxies, black holes, planets, life. And with those structures came higher entropy. But why did it start so low? That's one of the great mysteries. Some physicists think the laws of gravity may explain it, because gravity behaves differently from other forces, with clumping increasing entropy. Others think it points to something deeper we haven't yet understood. But whatever the explanation, that low entropy beginning is the reason anything has happened since. And it's still happening. Every process you see around you, waves crashing, leaves decaying, fireflies blinking, is part of entropy's gentle climb. Even when things seem to become more ordered, like a seed growing into a tree, the total entropy of the system and its surroundings still increases. The tree might be locally organized, but the energy it consumes and the waste it produces ensure that entropy overall keeps rising. Eventually, if the universe keeps expanding forever, it may reach a state called heat death. This is a hypothetical future where all energy has been evenly spread out, all stars have burned out, all processes have ceased. Everything would be in thermodynamic equilibrium, with maximum entropy and no way to do work. No gradients, no movement, no thought, just a quiet, cold stillness. That might sound bleak, but don't panic, it's a long way off. We're talking tens of trillions of years at least. Plenty of time to enjoy hot drinks, watch sunsets, and wonder at how a simple rule about disorder can shape everything. It's worth noting that entropy isn't just a destructive force, it's a creative one too. Complexity arises not in spite of entropy, but because of it. The universe finds new forms, new pathways, new structures as it moves toward disorder. Galaxies swirl, planets form, life blooms. None of this breaks the second law. It's all made possible by it. Entropy may guide the universe toward equilibrium, but it also allows for the temporary rise of islands of order. We are such an island. Conscious systems made of atoms, humming with heat, dancing on the edge of chaos and order. observers capable of understanding the very law that allows us to exist. So yes, entropy makes your coffee go cold and your ice cream melt, but it also powers the stars, drives evolution, and gives time its arrow. It's the quiet law behind every sunrise, every heartbeat, every falling leaf. The law that doesn't force anything, but makes everything possible. The law that never pauses, never skips a beat, and never forgets to let the universe unfold. In the beginning, the universe was a blazing soup of energy. No atoms, no molecules, no chemistry, just a chaotic tangle of particles too hot and frantic to hold hands. But then, as things cooled down, slowly, steadily over hundreds of thousands of years, a quiet miracle happened. The ingredients of the cosmos began to pair up. Protons caught electrons, atoms formed, and with that, the universe opened the door to chemistry, the ancient cosmic language of bonds, reactions, and eventually chocolate. But none of this was guaranteed. Chemistry only works because a very particular set of laws and constants happen to be just right. If even one piece were off, a force too strong, a particle too heavy, a constant slightly miscalibrated, then atoms might never have formed, or they might have been too unstable to stick together. Water wouldn't exist, carbon couldn't bond, you wouldn't be here, and neither would your favourite snack. So how did the universe manage to become a chemist? It all starts with the electromagnetic force. This is the attraction between opposite electric charges, protons and electrons for instance. It's a long-range force, unlike the strong nuclear force that only acts within the tiny confines of an atomic nucleus. And it's the glue that holds electrons near the nucleus, forming the basic structure of atoms. But it's not just about attraction. The electromagnetic force also repels like charges. That's important because protons packed inside a nucleus naturally want to fly apart. They're all positively charged, and without something stronger holding them together, the nucleus would simply explode. That's where the strong nuclear force comes in, a force that only kicks in at extremely short distances, but does so with impressive muscle. It overpowers the electromagnetic repulsion between protons and binds the nucleus together. Now, if the strong force were a little weaker, nuclei couldn't form. If it were stronger, fusion in stars might burn too fast, or create unstable elements. There's a narrow window where it works, just strong enough to bind, but not so strong that everything collapses into heavy elements before life has a chance to evolve. This balance is critical for chemistry because it ensures a wide variety of elements can exist, each with its own unique properties. Once you have stable atoms, the magic of the periodic table begins to emerge. Atoms vary based on how many protons they have. Hydrogen has one, helium has two, and so on. Each added proton brings a new electron along for the ride, and those electrons settle into distinct energy levels, or shells. These shells are where chemistry happens. Electrons want to be in the lowest possible energy state, but there are rules. Only a certain number of electrons can occupy each level, and they don't like to pair up unless they have to. This leads to atoms forming bonds, ways to share or trade electrons in pursuit of stability. Take water, for example. A single oxygen atom has 6 electrons in its outer shell, but it wants 8. Hydrogen has just 1 electron and wants 2. When 2 hydrogen atoms link up with 1 oxygen, they share their electrons and everyone ends up satisfied. The result is a molecule that's stable, polar, and astonishingly useful. Water isn't just good for drinking, it's a perfect solvent, capable of dissolving ions, transporting nutrients, and regulating temperature. It's the backstage manager of life on Earth. Or consider carbon. It has 4 electrons in its outer shell, which makes it wonderfully flexible. It can bond in all directions, forming chains, rings, and lattices. This versatility is what allows for the rich complexity of organic chemistry, the branch of chemistry responsible for cells, proteins, DNA, and dinner. Carbon is the ultimate team player in the molecular world, happy to form double bonds, triple bonds, and even giant frameworks like graphene or diamonds. But none of this would be possible if the mass of the electron were too different, or if the electric charge of the proton weren't precisely balanced by the charge of the electron. Even the strength of the electromagnetic interaction, the fine structure constant, must be within a very specific range for atoms to behave the way they do. Too strong, and electrons crash into the nucleus. Too weak, and atoms can't hold together. Even the neutron, that quietly neutral particle inside the nucleus, has a role to play. It helps stabilize atoms by adding mass and keeping the positively charged protons from flying apart. But if neutrons were just a little lighter, they wouldn't stick around. If they were heavier, hydrogen might never form. The fact that neutrons are slightly heavier than protons is what allows for the stability of hydrogen, the most abundant and essential element in the universe. Then there's the fact that chemistry actually works over a huge range of scales. Atomic forces govern tiny distances, but they give rise to macroscopic phenomena. A single oxygen molecule behaves the same way in your lungs as it does in the atmosphere of Jupiter. That kind of consistency is only possible because the laws of physics and the constants that define them apply everywhere. Chemistry is universal. The same rules that form rust on Earth are busy shaping clouds on Venus and ice on Pluto. This universality is also why we think life might exist elsewhere. Because if chemistry works here, it probably works out there too. Maybe not in quite the same way. Alien biochemistry might use silicon instead of carbon, or ammonia instead of water. But the underlying principles remain. Electrons still want to be stable. Atoms still want to bond. The drive toward a chemical equilibrium is a rule that knows no borders. On a more poetic level, chemistry is what allows the universe to be expressive. It's not just atoms bouncing around randomly, it's patterns, preferences, and reactions. It's the reason fireflies glow, why leaves change colour in autumn, and why your morning toast smells like comfort. Chemical bonds can store energy, release it, absorb light, reflect it, or give it away in little packets of heat. They allow for memory, sensation, transformation. Chemistry is physics with personality. And yet, for all its variety, chemistry is ultimately just the application of a few basic rules. Charges attract, electrons seek stability, energy tends toward lower states. These principles, simple, elegant, reliable, combine in countless ways to build everything from stardust to soufflés. The universe didn't have to allow for any of this. It could have remained a sea of particles endlessly drifting. It could have clumped into black holes and forgotten the possibility of structure, but instead it cooled just right, balanced its forces just so, and let the atoms begin to dance. And out of that dance came molecules, out of molecules came cells, and eventually out of those cells came thoughts like, I wonder why chocolate tastes so good. The answer, of course, lies in chemistry, in the way sugars and fats interact with taste receptors, in the way molecules trigger dopamine in the brain. But underneath all of that, beneath the enzymes, beneath the carbon bonds, are the laws of physics quietly making the whole thing possible. The rules didn't just give us stars and space. They gave us flavour. They gave us life. They gave us a universe where atoms can not only exist but fall in love, bond and build something more, and in doing so they made room for a very strange species to look around, take a bite of something sweet, and whisper, "This is amazing." The universe has a talent for doing a lot with a little. Take a few simple rules, set them in motion, and suddenly, snowflakes, tornadoes, brains. It's one of the most beautiful and baffling ideas in science, emergence. The notion that complex organized structures can arise from simple components following basic rules. No central planner, no grand design, just the spontaneous unfolding of patterns from the ground up. At first glance it sounds almost magical. How do atoms, which don't think or plan or feel, combine to create consciousness? How does a simple fluid become a hurricane? How does a pile of sand know when it's a sand dune? But emergence isn't magic, it's mathematics in action. It's physics discovering that the sum can be vastly more than the parts. That simplicity, when multiplied, twisted, and layered just right, can give rise to breathtaking complexity. Start with a snowflake. It's a six-sided crystal made entirely of water molecules, each following straightforward rules about how they bond. There's no snowflake architect deciding where the next ice crystal should grow. Instead, the shape emerges from temperature, humidity, and the way water molecules arrange themselves under changing conditions. The result? Endless variety. No two snowflakes are exactly alike, even though they're built from the same ingredients obeying the same rules. Or consider flocking birds. Each bird doesn't know where the group is going, it just follows a few simple rules. Avoid crashing into neighbours, stay roughly the same distance from others, align your direction. That's it. But from these local behaviours emerges a coordinated, swirling ballet across the sky. A murmuration, weaving and folding like a single living thing. This is the essence of emergence, local interactions giving rise to global behaviour. No conductor, no master plan, just individual units reacting to their environment, creating unexpected order on a larger scale. In physics and chemistry, emergence shows up all the time. Atoms, for instance, are governed by quantum rules. But when you pile trillions of them together, new behaviours appear, things like temperature, pressure, and conductivity. You can't point to a single atom and say, this one is hot. Temperature only makes sense when you look at the statistical motion of a vast collection of particles. Likewise, a single water molecule doesn't have wetness, but when enough of them flow together, they become a stream. With flow comes viscosity, turbulence, surface tension, all emergent properties that don't exist at the microscopic level. One of the most striking examples is life itself. Cells are just bags of molecules. Those molecules are made of atoms, and those atoms obey the basic laws of physics, interactions between charges, the push and pull of energy gradients. But somehow, when arranged just right, they form something that eats, moves, adapts, and reproduces. Life emerges not because the atoms are special, but because the patterns they form are. And then from life emerges mind. Your brain is made of about 86 billion neurons, each one a specialized cell that passes electrical and chemical signals. A single neuron isn't conscious. It doesn't know anything. It just fires when it receives input. But when those billions of neurons fire in a coordinated way, consciousness emerges. Thoughts, emotions, the ability to reflect on your own existence and wonder about snowflakes. No single part of your brain contains your mind. There's no central neuron labelled self. Instead, consciousness seems to be an emergent property, a collective result of countless interactions happening in real time. This kind of complexity from simplicity isn't limited to biology. Even in purely physical systems, emergence plays a role. Consider superconductivity, the phenomenon where some materials conduct electricity without resistance. It only happens under certain conditions, and it's not something you can predict by looking at just one electron. It emerges from a coordinated dance of particles, a kind of quantum choreography. Or think about phase transitions. Ice melts, water boils, iron becomes magnetized. These shifts happen not because the particles themselves change, but because their collective behavior crosses a threshold. Suddenly, new properties emerge. A magnet isn't just a collection of iron atoms, it's a material where all the tiny magnetic moments line up, producing a unified field. Even space-time itself might be emergent. Some physicists suggest that space and time aren't fundamental, but arise from deeper quantum entanglements or informational networks. In this view, space-time is like the surface of water. It looks smooth and continuous, but underneath might be something granular, tangled, and far stranger than we can currently imagine. What makes emergence so fascinating is that it gives us a way to bridge the gap between laws and lived experience. The universe may be governed by a small set of physical principles, But those principles don't just repeat the same patterns over and over. They scale, they combine, they self-organize, and in doing so, they produce structure, novelty, and beauty. It also means we can't always predict large-scale outcomes from small-scale rules. Just knowing the laws isn't always enough to foresee the result. You can write down the rules for a flock of birds, but you can't predict exactly what shape they'll take in the sky. You can simulate weather with incredible precision, but there's a limit to how far ahead you can forecast. Complexity emerges not from chaos, but from the non-linear ways things interact. Emergence teaches us humility. It reminds us that even simple things can produce surprises, and that not all behaviour can be reduced to isolated parts. It also gives us hope that the world isn't a cold, deterministic machine, but a place where the unexpected can arise, where music, cities, ecosystems, languages, and minds can emerge from matter obeying rules as old as the universe itself. And perhaps most wonderfully, emergence is still unfolding. Evolution didn't stop at single-celled organisms, chemistry didn't stop at methane and ammonia. The rules are still running, still combining, still surprising us. Somewhere in the universe, new forms may be emerging even now, new ways for matter to organize itself, for complexity to arise, for structure to bloom in unlikely places. So the next time you see a snowflake, or watch leaves flutter in the wind, or find yourself lost in thought about nothing in particular, remember, all of it is emergence in action. A universe that writes complexity out of simplicity, that makes patterns from particles, that turns rules into reality, not with force, but with quiet, intricate grace. On Earth, we're fairly confident that apples fall down instead of up, light travels at its usual pace, and electrons don't suddenly decide to take a holiday from behaving like electrons. The rules of physics, these quiet, invisible constraints, seem remarkably consistent. But here's the big question. How do we know that the same laws apply far beyond our solar system, or even beyond our galaxy? Is it possible that somewhere out there on the far side of the cosmos, nature plays a different game entirely? It's an unsettling thought, especially for physicists who like their equations to work universally. But it's also an important one. The entire structure of science rests on the assumption that the laws of physics are not local quirks but universal truths. That gravity behaves the same on Alpha Centauri as it does in your kitchen. That photons don't take shortcuts in other galaxies. That the constants we've carefully measured here, like the speed of light or the mass of an electron, hold up across billions of light years. And for the most part, the evidence says, yes, they do. Let's start with light. When we look at distant galaxies, so distant their light has taken billions of years to reach us. We're effectively peering back in time. And what do we see? Spectral lines, specific fingerprints in the light, caused by electrons jumping between energy levels in atoms. These lines are the same ones we measure in labs on Earth. Hydrogen emits the same signature glow, whether it's in a lab flask or swirling in a nebula 10 billion light-years away. This suggests that the rules governing atomic behaviour, electromagnetic forces, electron mass, Planck's constant, haven't changed. If they had, those spectral lines would shift or blur. We'd see alien fingerprints. But we don't. The universe seems remarkably consistent. Now it's true that we've found tiny hints, just hints, that some constants might vary slightly across vast distances or time frames. The fine structure constant, that mysterious number close to 1/137, appears to show a very slight variation in some observations. Not enough to rewrite physics just yet, but enough to raise eyebrows and keep telescopes busy. Still, even those possible variations are incredibly small. If the laws are changing, they're changing very, very slowly or very, very subtly. For now, the safest bet is that physics is uniform across the observable universe, the same rules everywhere we can see. But what about beyond what we can see? The observable universe is vast, but it's not infinite. It stretches out about 46 billion light-years in every direction, limited not by the size of space itself, but by the age of light. That's as far as light has had time to travel since the beginning of the universe. Beyond that, well, we just don't know. There could be more galaxies, more stars, maybe even more copies of you and me in slightly different configurations. But could there be regions where the laws of physics are different? It's not a ridiculous idea. In fact, some versions of cosmic inflation, the rapid expansion thought to have happened just after the Big Bang, suggest that our universe might be just one bubble in a vast multiverse. In this view, other bubbles could have different vacuum energies, different constants, different rules entirely. Maybe gravity is stronger in one bubble, or electromagnetism is weaker, or time flows in loops. That might sound like science fiction, but it's an actual, if speculative, consequence of some cosmological models. It doesn't mean we'll ever reach these other regions. Most are probably permanently out of reach. But it does mean the notion of a universal law might be more local than we hoped. Still, within our cosmic bubble, the evidence points to remarkable uniformity. The cosmic microwave background, the afterglow of the Big Bang, looks almost exactly the same in every direction. The slight variations we do see are consistent with early quantum fluctuations, not different laws of physics. Galaxies form in familiar patterns. Stars follow predictable lifespans. Supernovae explode according to the same equations, whether they're near or far. In fact, the entire science of cosmology relies on what's called the cosmological principle. It assumes that on large scales the universe is homogeneous and isotropic, basically the same everywhere and in every direction. It's an elegant idea, and so far it's held up surprisingly well. But physics isn't satisfied with so far. Scientists keep looking. They test the constancy of fundamental constants across time and space. They study gravitational waves, high-energy cosmic rays, and the behavior of light from quasars. They even use ancient starlight to probe whether the electron-to-proton mass ratio has changed over billions of years. And here's a delightful twist. The fact that we can do this at all is itself evidence of physical law being consistent. If light behaved differently across the universe, we wouldn't be able to read those distant signals in the first place. The very tools we use to investigate the question are based on the assumption that the rules don't change mid-game. This all raises a philosophical point too. When we ask whether the laws of physics are the same everywhere, we're really asking something about the nature of reality itself. Are these laws discovered or created? Are they woven into the fabric of existence, or are they emergent from something deeper? If the laws can vary, what chooses which version goes where? And if they can't vary, if they're truly immutable, then we're living in a universe where every snowflake, every heartbeat, every distant star is part of a single unbroken logic. A cosmic grammar spoken fluently across space and time. For now, we live in a universe that, despite its vastness, behaves like one big connected system. The same hydrogen that fuels our sun also lights the stars in distant galaxies. The same gravity that keeps your feet on the ground is sculpting galaxies millions of light years away. The same light that bounces off your book also travelled to Earth from the edge of the known universe without changing its stripes. It's a comforting thought that we're not just in a remote pocket of rules, but part of something unified, harmonious, and consistent. A cosmos where the laws don't play favourites, where the same equations govern the birth of a planet and the boiling of your tea. But that doesn't mean we've reached the end of the story. Physics is still searching, still asking. What if there are subtler differences we haven't noticed yet? What if deeper rules are hiding beneath the surface, shaping the familiar ones in ways we've only begun to glimpse? Until then, we gaze into the distance, watching the flicker of ancient starlight, each photon a traveller from another corner of the universe whispering, "It's all the same here too." There's something comforting about the idea that the laws of physics are permanent, that gravity has always worked the same way, that the speed of light hasn't changed since the first flicker of existence, and that the constants we measure today are as timeless as the stars themselves. But physics, like everything else in the universe, has learned to keep a curious eyebrow raised. Because what if? The laws aren't eternal. It sounds like a radical idea, but it's one scientist takes seriously. The notion that the rules of the universe might evolve, slowly, subtly, almost imperceptibly over time, has cropped up in everything from string theory to cosmology. And while the evidence is far from conclusive, it's worth pondering. After all, if the laws of physics did change over cosmic time, what would that mean for the future of the universe? And what might it tell us about the past? Let's begin with the constants. Physical laws are often expressed through equations, and those equations include numbers that don't seem to come from anywhere else. The speed of light, the gravitational constant, Planck's constant, the fine structure constant. These are not just measurements. They are the numbers that set the scale for how the universe operates. Take the fine structure constant. It's a dimensionless number, approximately 1 over 137, that determines the strength of the electromagnetic force. It affects how atoms hold together, how light interacts with matter, and even how stars burn. If it were just a little different, chemistry wouldn't work, life wouldn't be possible, and your toaster might be a black hole, that kind of thing. Now, imagine that number changing, not drastically, not suddenly, but drifting, ever so slightly over billions of years. What would we expect to see? One approach to this question is to look back in time. Astronomers do this by analysing light from distant galaxies. Since that light has been travelling for billions of years, we're essentially peering into the ancient universe, and in that light we can look for tiny shifts in spectral lines, fingerprints of atomic interactions. If the fine structure constant were even minutely different long ago, those lines would be in slightly different places. And here's where things get interesting. Some studies suggest there might be a small variation in the fine structure constant when comparing light from opposite ends of the sky. It's a tiny effect, well within the margin of error, but it has raised a few scientific eyebrows. Could it be noise? A quirk of measurement? Absolutely. But it could also be a hint that the laws aren't carved in cosmic stone. Another place to look is the gravitational constant, known affectionately as Big G. It determines the strength of gravity, the way mass pulls on other mass. If G were stronger or weaker in the past, it would have affected everything from the orbits of planets to the life cycles of stars. And if it were slowly changing even now, the universe's expansion rate might not match our predictions. Researchers have examined ancient astronomical records, like eclipse timings recorded thousands of years ago, and compared them to modern models. So far, they haven't found strong evidence of change in G. But the uncertainty still allows for a tiny rate of drift. So small it wouldn't affect us now, but might matter over billions of years. Why would constants change at all? One idea comes from certain models in theoretical physics, especially those involving scalar fields. These fields can vary across space and time, and if they couple to physical constants, they might slowly alter the values we measure. It's like the universe has background settings, and some of those sliders might not be perfectly locked in place. In some versions of string theory, the laws of physics aren't universal. They depend on how extra dimensions are curled up. As the universe evolves, the geometry of these hidden dimensions might shift, leading to small changes in the values of constants in our familiar four-dimensional spacetime. Another perspective is cosmological. As the universe expands and cools, it undergoes phase transitions, a bit like water freezing into ice. In the early moments after the Big Bang, forces that are now distinct, like the electromagnetic and weak nuclear forces, were unified. As the universe cooled, they separated, each acquiring their own behaviour and constants. Who's to say the process has stopped entirely? Perhaps further transitions lie in the future, with new physics waiting to unfold. Now, if the laws do change over time, even very slowly, that would have deep implications. For one thing, it would mean that reality is not static but dynamic. not just in content, but in form. The very canvas on which existence is painted would be shifting, like a movie that rewrites its own plot mid-screening. It would also mean that predictions become a little less certain. Imagine building a starship using physics from today, only to find that by the time you reach another galaxy, the laws have shifted just enough to make your fuel cells useless. An extreme example, yes, but conceptually relevant. There's a philosophical ripple too. If the laws evolve, then perhaps they're not fundamental in the way we usually think. Maybe they're emergent properties of deeper processes, like rules that arise from the behavior of an even more primitive system. The laws might be the visible patterns on a deeper shifting fabric. On the flip side, if the laws are truly eternal, unchanging from the first Planck tick to the final whisper of cosmic darkness, that's remarkable too. It suggests that the universe is built on foundations of astonishing stability, that for all its chaos and noise, the cosmos is rooted in unwavering principles, like a symphony that never skips a beat, even as its melodies evolve. Either way, we win. If the laws are fixed, then we live in a universe of rare elegance and predictability. If they change, we inhabit a living, evolving cosmos where new patterns may yet emerge, and surprises are part of the blueprint. And of course, even if constants do vary, they likely do so at a rate far too slow for daily life to notice. Your morning coffee will still brew, apples will still fall, light will still travel at light speed, give or take a few decimal points that no barista or cat will care about. In the end, the idea that the laws might evolve is not just a curiosity, it's a gentle reminder that even the firmest truths we know may have a story behind them, that the universe may be more like a conversation than a decree, and that whether written in stone or whispered by time, the rules that govern it are still being read, measured and understood, one star, one particle, one slow tick at a time. Picture the smallest things in the universe, not pebbles, not cells, not even atoms, but the particles inside those atoms, electrons, quarks, neutrinos, the tiny jittery citizens of the quantum realm. And here's what's fascinating. They never disobey. Not once. An electron doesn't one day decide to orbit the nucleus backwards. A photon doesn't take a shortcut through space. Even the most mischievous-sounding particles, muons, gluons and charm quarks, are rule followers to a fault. But who or what makes sure of that? In the grand stage play of physics, there's no off-stage manager waving a clipboard, no cosmic referee issuing yellow cards to unruly bossons. Particles simply do what they do, exactly as prescribed by the laws of nature. It's not that they choose to follow the rules, they are the rules, or rather their behaviours emerge inevitably from the rules. Let's start with the basics. When we say particles follow the laws, we're usually talking about quantum fields. In modern physics, every particle is actually an excitation, a ripple, in a fundamental field. The electron field, for example, fills all of space. What we call an electron is just a little blip of energy in that field. That's why every electron in the universe behaves exactly the same. They have the same mass, the same charge, the same magnetic moment. Because they are all manifestations of the same underlying thing. And that thing, the field, is governed by mathematical equations, not optional suggestions, unbreakable laws. It's a bit like musical notes on a violin string. You can't just pluck a random tone. Only specific vibrations produce stable notes. Similarly, particles can only exist in certain states, because those are the stable notes of their fields. So when an electron orbits an atom, it's not deciding how to behave. It can only exist in discrete energy levels, defined by solutions to the Schrödinger equation. These aren't guidelines. They're the only possibilities. The universe doesn't allow improvisation here. But this brings us to a deeper question. Why are these laws so precise? Why do they never glitch? If the cosmos is a kind of computer, where's the code? And if it's not a computer, how does it know how to act? One way to think about this is through symmetry. In physics, symmetry isn't just visual. It's a deep mathematical principle. It means that if you shift your point of view, move in space, rotate in time, or flip directions, the laws don't change. And from these symmetries through something called Noether's theorem emerge conservation laws. Take energy conservation. The reason energy can't be created or destroyed is because the laws of physics don't change over time. That symmetry gives rise to the rule. Similarly, momentum conservation comes from space being uniform. The rules are tied to the symmetries, and the particles, they're built on those rules. Which means, in a poetic way, particles obey because the universe itself is structured that way. It's not that someone enforces the law, it's that disobedience is literally impossible. The quantum field doesn't even contain instructions for rebellion. Still, it's hard not to marvel at the consistency. A single photon emitted from a dying star on the far edge of the universe will travel for billions of years, crossing untold voids, brushing past galaxies, maybe even curving slightly around black holes, only to reach your eye and trigger a chemical response in your retina, precisely as it should. The particle never once deviated from its expected path, never aged, never wobbled off script. This reliability is what makes physics so powerful. It lets us build theories that not only explain what we see, but predict what we haven't yet seen. We can shoot electrons through magnetic fields and know exactly how they'll curve. We can measure how atoms absorb and emit light, and trust that every atom of hydrogen in the universe will sing the same spectral tune. In fact, this obedience is what allows the universe to have structure at all. If particles were even slightly unreliable, atoms couldn't form, chemistry would be chaos, stars couldn't shine steadily. Life, if it arose at all, would be subject to random quantum mood swings. The fact that reality doesn't flicker in and out of order is a quiet miracle of precision. Now you might wonder, is this obedience absolute? Aren't there quantum events that are random? That's a fair question. Quantum mechanics does include randomness. When a particle decays, or when a photon hits a detector, the outcome isn't always certain. But here's the twist. The randomness is predictable. That sounds like an oxymoron, but in quantum physics, the probabilities themselves follow strict rules. Take radioactive decay. We can't say when a specific atom will decay, but we can say how many out of a group will decay in a given time. The statistics follow a precise exponential curve. It's like rolling dice that never cheat on the probabilities. Even uncertainty in the quantum world has a mathematical backbone. In that sense, particles don't break the rules. They are the rules. Their behaviour is the law unfolding in space and time. There's no need for enforcement, because deviation isn't part of the equation. Still, the question lingers. Why is it this way? Why does nature seem to favour mathematical elegance? Why not a universe where things occasionally glitch, just to keep us on our toes? Some physicists think there may be a deeper layer still, something more fundamental than even quantum fields. Perhaps information is the bedrock of reality, and particles are just emergent patterns. Or perhaps the laws we know are part of a wider landscape, and our universe just happens to be in a region where order wins out over chaos. There's also the anthropic perspective. If particles didn't obey the rules so perfectly, we wouldn't be here to ask about it. In a universe where electrons had existential crises, molecules wouldn't form, stars wouldn't shine, and brains wouldn't work. So maybe we live in a lawful universe simply because only lawful universes support the emergence of curious life forms, wondering why everything behaves so well. Whatever the reason, it's hard not to feel a quiet awe. Every breath you take, every photon bouncing off your surroundings, every atom in your body, all of it is held together by particles that never ever break the rules. No matter how strange, chaotic, or unpredictable the world may feel, down at the quantum level, there is astonishing, unwavering order. So the next time you drop your keys and they fall predictably to the floor, or you marvel at the colours in a soap bubble, or you look up at the stars and realise they're powered by hydrogen atoms, behaving exactly as they must, take a moment to appreciate the loyalty of the universe. The particles aren't performing for us. They're just being themselves, obedient, predictable, perfectly, invisibly disciplined. Imagine you're standing still on a quiet road, watching a train glide by. Someone on that train is tossing a ball straight up into the air. To them, the ball simply rises and falls right back into their hand. But to you, standing on the platform, that same ball traces a strange arc through the air, a parabolic path, moving forward as it goes up and down. Two observers, two very different views of the same event. Yet the laws of physics? Completely unbothered. They work just as smoothly for both of you. This remarkable quality, the ability of physical laws to stay the same no matter who's looking or how fast they're moving, is called invariance. And though it sounds like something quietly sipping tea in the background, invariance is actually one of the most powerful ideas in all of science. It's what lets physics remain consistent, no matter where you are, when you are, or how you're moving. Let's take a simple example. Newton's second law, force equals mass times acceleration, doesn't change if you're riding a train at a steady speed. If you push a ball forward with your hand, it behaves the same whether you're on the train or at home in your kitchen. That's because the laws of mechanics are invariant under what physicists call Galilean transformations, shifting your frame of reference by a constant velocity. Now crank things up a notch. What if you're not just moving slowly in a train, but approaching the speed of light in a spaceship? That's where Einstein enters the scene with his theory of special relativity. It tells us that even at high speeds, the laws of physics, including the speed of light, stay exactly the same for every observer, no matter how fast they're going. That's a mind-bending idea. It means time itself can tick differently depending on your motion. Lengths can contract, clocks can disagree. But no matter how distorted the experience may seem, the underlying equations, those precious sacred laws, don't blink. They're invariant under Lorentz transformations, the relativistic version of those train platform shifts. And this isn't just a mathematical trick, it's an essential pillar of how the universe holds together. If physics weren't invariant, we'd be in serious trouble. Imagine if Newton's laws only worked on Mondays, or if the speed of light changed depending on which direction you were facing. Navigation systems would fail, chemistry would become unpredictable, and the entire premise of doing science, that the rules are consistent and discoverable, would fall apart. Invariance gives us trust. It means that when we launch a probe to Saturn, the same physics that guided it here on Earth will keep guiding it millions of kilometers away. It means that when we study atoms in a lab, we're also learning something true about stars. In a way, invariance is the fairness doctrine of the cosmos. No one gets special treatment. No perspective is privileged. Physics is blind to your coordinates. But there's another layer to this, and it's where things get even more beautiful. Invariance doesn't just keep the rules consistent, it actually generates some of the rules. Enter Noether's theorem, one of the most elegant results in mathematical physics. Named after Emmy Noether, a brilliant German mathematician working in the early 20th century, the theorem tells us that for every symmetry in nature there's a corresponding conservation law. What does that mean? If a law of physics doesn't change over time, then energy must be conserved. If the laws don't change when you move from one place to another, then momentum is conserved. If they don't change when you rotate your experiment, then angular momentum stays constant. In other words, the unchanging nature of the laws creates the things that stay the same. Conservation isn't an accident, it's the consequence of invariance. Let that settle for a moment. The fact that your morning coffee doesn't suddenly fly off the table when you turn around isn't just good luck. It's a manifestation of the rotational symmetry of space. The way your feet stay firmly planted on Earth, no matter what direction you're facing, is a quiet echo of the universe's underlying consistency. And this goes beyond just space and time. There are deeper symmetries, abstract ones, that govern the behavior of particles. Quantum fields have symmetries too, and these determine the fundamental forces. The invariance of the electromagnetic field leads to the conservation of the electric charge. The invariance of the strong nuclear force leads to color charge conservation among quarks. These are not just pretty patterns, they are the scaffolding of physical reality. Of course, not all symmetries are perfect. Some are broken. In fact, the breaking of certain symmetries gives rise to the diversity of particles and masses we see in the universe. If every symmetry were perfect, everything might be the same. No atoms, no chemistry, no stars, no variety. But the existence of symmetry, even when it's broken, still provides the backbone. It defines what's possible. You could say that invariance gives the universe its rhythm. It lets the dance go on without interruption, even if the steps get more complicated. It allows for creativity within a framework, like jazz improvisation built on a stable chord progression. And from a philosophical point of view, invariance is deeply reassuring. It says the universe isn't random, that behind all the complexity and chaos, there are simple truths that don't budge, that no matter how far you drift in time or space, you're still playing by the same rules. You're still part of the same cosmic conversation. Even light, with all its shimmering complexity, follows this principle. No matter who's watching, no matter how fast they're moving, the speed of light remains the same. It's the anchor point of Einstein's relativity, the great invariant, whispering the same value to every observer across space and time. So what holds the universe together? It's not just forces or particles or equations, it's invariance, the quiet insistence that the laws remain the same no matter who's watching, the idea that reality plays fair, that truth doesn't depend on your position or your pace. And in a world that often feels chaotic or confusing, there's something soothing about that. To know that beneath the noise there are principles that don't change, that whether you're on a train or a planet or drifting in the void between galaxies, the universe is still speaking the same language. It's a soft, unwavering hum, the calm beneath the storm, the quiet power that makes everything else possible. Invariance. Not loud, not flashy, but absolutely essential. Imagine standing on a trampoline holding a bowling ball. You gently place it down in the middle, and suddenly the surface dips, curving inward. Now roll a marble along the edge, and you'll see it spiral toward the centre. Not because the ball reached out and grabbed it, but because the fabric itself told the marble where to go. This simple image is one of the most famous metaphors in modern physics. It's not perfect, of course, but it hints at something profound. Gravity isn't a force in the traditional sense. It's the result of curved space-time. This idea, that mass and energy warp the geometry of the universe, and that objects move through that geometry like boats in a current, was Einstein's great revelation. In 1915, he unveiled his general theory of relativity, and with it, a radically different way of understanding gravity. No longer was gravity a mysterious pull from a distance. Instead, it became a matter of shape, of curves and paths, of the fabric of space and time bending around mass. And here's the elegant twist. This isn't just a poetic metaphor. It's literally the rulebook the universe follows. Let's unpack that. First, what exactly is space-time? You might be tempted to think of space and time as separate things, space as where stuff is, and time as when stuff happens. But in physics, they're inseparable. They form a four-dimensional continuum, 3 dimensions of space and 1 of time, stitched together into a single entity. Imagine plotting the motion of a planet on a graph. Its position in space changes as time goes on. In the language of space-time, that motion traces a line called a world line. And here's the magic. That world line isn't drawn on a fixed grid. The grid itself bends and warps, depending on how mass and energy are distributed. In flat space-time, no nearby stars, no planets, no gravity. An object in motion just keeps moving in a straight line. But near a massive object, space-time curves, and those straight lines become geodesics, the equivalent of straightest possible paths through curved geometry. Planets orbit the sun not because they're being tugged, but because they're following the natural curves laid down by the sun's mass. Even light, which we usually imagine as the ultimate speedster, follows these paths. When it passes near a massive galaxy, its path bends, not because it's being pulled, but because the space it travels through is itself curved. This effect, called gravitational lensing, has been observed countless times. It's like nature's own telescope, where light from distant galaxies is bent into arcs and rings by the mass of other galaxies in front of them, and that's just the beginning. When Einstein presented this vision of gravity, it was wildly different from Newton's version, which had worked perfectly well for centuries. But Einstein's equations, beautiful, dense, and a little terrifying, offered something deeper. They didn't just describe how gravity behaves, they described how space and time themselves respond to the presence of energy. The rules had become the landscape. You might ask, if space-time is like a fabric, what is it made of? That's a tricky question, and one without a clear answer. Space-time isn't a substance you can scoop into a jar. It's more like the stage on which all things play out, and sometimes the stage itself moves and dances. In fact, that's exactly what happens during a gravitational wave. In 2015, scientists detected a faint ripple in space-time, caused by the collision of two black holes over 1 billion light-years away. The wave passed through Earth, stretching and squeezing space itself by a fraction of a proton's width. It was tiny, it was subtle, but it confirmed a prediction Einstein had made a century earlier. Think about that. A pair of dead stars spiraling into one another sent out waves, not of sound, not of light, but of space-time itself. And over 1 billion years later, that ripple gently wobbled a detector here on Earth, proving that space-time isn't just a passive arena. It's dynamic. It breathes. It responds. This leads to a fascinating idea. The geometry of the universe is the law. There's no need for an external force to govern how things move. Instead, movement arises naturally from the shape of space-time. If you know the geometry, you know everything. And yet this elegant picture is still incomplete. While general relativity explains gravity beautifully, it doesn't play well with quantum mechanics. At the tinier scales, where particles jitter and fields fluctuate, space-time's smooth fabric begins to look more like foam. Tiny bubbles, loops and fluctuations, quantum gravity, if it exists, hasn't yet handed us a full equation. But that's part of the wonder. We're living in a universe where the rulebook is not just written on paper, it's etched into the very structure of reality. The planets trace their orbits not because they've memorized formulas, but because the space they inhabit bends in just the right way. A falling apple, a drifting comet, even the trajectory of your morning coffee as you raise it to your lips, all of it follows the quiet curves of space-time. There's something deeply calming in that the chaos of life unfolds against a backdrop of geometric order, that beneath the surface of motion and change lies a serene architecture, a kind of invisible scaffolding shaped by mass, energy, and the passage of time. And here's a gentle curiosity. You are part of that fabric too. Your body, your thoughts, your dreams, all exist in space-time, shaping it ever so slightly. Yes, even your mass curves the geometry around you, just a smidge. You might not notice it, but space-time notices you. So the next time you look up at the moon, or feel your feet firmly planted on the ground, remember, you're not being pulled down. You're following the lines written in the curvature of space and time. You're moving, even while still, along a path drawn by the mass of the Earth and the laws that shaped it. It's not just gravity, it's geometry, and it's beautiful. Let's take a slow breath and think about something that surrounds us completely, yet always seems just out of reach. Time. It ticks by without asking for permission. It never repeats itself exactly, and it gently nudges everything from teacups to galaxies toward change. But what is time, really? Is it a fundamental part of reality, like space and mass? Or is it something softer, a side effect of other processes, an illusion stitched together by memory and perception? To most of us, time feels obvious. Events happen in a certain order. The sun rises, then sets. You wake up, go about your day, and eventually sleep again. A dropped mug shatters, but a shattered mug never leaps off the floor and reassembles itself. There's a before and an after, a past you can remember, and a future you can only guess. But for physics, especially the deepest levels of it, this intuitive flow of time is surprisingly hard to pin down. At the level of basic equations, time is curiously symmetrical. Newton's laws of motion work just as well if you run them backward. A video of planets orbiting a star could be played in reverse and still look physically correct. Even the quantum world, with its oddities and probabilities, generally doesn't care which way the clock runs. Most of nature's rules are time neutral. That might seem unsettling. If the laws allow for time to run in either direction, why does it always seem to go forward? Why don't we age in reverse, or unbreak our dishes, or remember tomorrow before yesterday? The answer lies in a concept called entropy. Entropy is a measure of disorder, of how mixed up or random a system is, and according to the second law of thermodynamics, entropy tends to increase over time. A neat deck of cards becomes a messy pile, not the other way around. Eggs scramble, but don't unscramble. Ice melts, but doesn't refreeze in your glass spontaneously. These changes are overwhelmingly more probable in one direction. This rise in entropy is what gives time its arrow. It's not that time itself is marching forward. It's that the universe is transitioning from states of low entropy to high entropy. The early universe was smooth, ordered, and surprisingly tidy. Since then, things have been getting messier. Stars forming and dying, galaxies clumping, life evolving, and coffee growing cold. Entropy, then, might be the closest thing physics has to a one-way sign. It gives time its direction, not by decree, but by probability. The universe prefers disorder, not out of laziness, but simply because there are more ways to be disordered than ordered. A shuffled deck has more possible combinations than a perfect sequence. But there's more to time than just entropy. Our own perception plays a role too. Your brain stitches together a flowing sense of time from moments, memories, and changes. When nothing happens, no motion, no sensation, your perception of time can stretch or vanish entirely. This is why time seems to slow when you're bored and speed up when you're having fun. It's also why dreams can seem endless, even if they last just a few minutes. In a sense, time is a story your mind tells itself, and like all good stories, it has a beginning, a middle, and an end. That structure is comforting, but it might not reflect the underlying nature of reality. Some physicists argue that the universe doesn't evolve through time like a film strip, frame by frame. Instead, all moments might exist simultaneously, like pages in a book, past, present, and future, all there at once. We just happen to be reading one page at a time. This idea, called the block universe or eternalism, is a perspective that treats time as another dimension, one you move through, just like space. From this viewpoint, your birth, your best ideas, your quietest thoughts, and your final moments all exist as fixed coordinates in a four-dimensional space-time. Nothing changes. It's just that your consciousness is sliding along the path. Of course, that raises some big philosophical questions. If time is just another dimension, do we really have free will? Or are we just passengers on a predetermined route? Does the future already exist? Can we, in any meaningful way, change it? Some scientists push back against the block universe, arguing instead for presentism, the idea that only the present moment is real. The past is gone, and the future hasn't yet arrived. From this view, the flow of time is genuine and meaningful. The universe is still unfolding, and you're helping it do so. There's also a middle ground known as growing block theory, which says the past and present exist, but the future does not. The block is still growing, moment by moment, like fresh pages being written. No one knows which view is right. They're all attempts to explain something we experience constantly, but understand only vaguely. One thing that complicates the matter further is relativity. Einstein showed that time is not universal. It can stretch and shrink depending on your speed and gravity. A clock on a mountaintop ticks slightly faster than one at sea level. An astronaut moving quickly will age more slowly than someone on Earth. Time is not fixed. It is flexible, relative, woven together with space. This leads to some fun but real consequences. In principle, if you could travel near the speed of light and come back, you might find that decades have passed for those you left behind, while you've aged only a few years. Time travel to the future, in a sense, is possible. It is built into the structure of the universe. But going back in time, that's trickier. Most theories don't allow it without invoking bizarre constructs like wormholes or cosmic strings. And even then, paradoxes creep in. If you went back and changed the past, what would happen to the future? Would it rewrite itself? Would there be multiple timelines? Many physicists believe that these time travel paradoxes point to a deeper truth, that the past is fixed, the future uncertain, and time only moves forward because that's the direction in which entropy increases and memories accumulate. So is time real? Yes and no. Time is as real as motion, as temperature, as love or sadness. It's part of the way we experience change. But whether it exists out there in the same way a rock does, that's still up for debate. What we do know is that time isn't something we carry in our pockets. It's built into the universe. It hums beneath every heartbeat, every flicker of light, every crumbling mountain and blooming flower. It lets things happen, lets stories unfold, lets existence have rhythm, and maybe that's the most comforting thing of all. Whether time is a law or an illusion, whether it flows or stands still, it gives us structure. It gives us before and after. It gives us meaning. So as the minutes slip by and your eyes grow heavier, remember, you're surfing the gentle slope of entropy, riding the wave of a universe that makes space for change. You're part of time, and time is part of you. Even in stillness, you're moving through something vast and quiet, something old, mysterious, and possibly more beautiful than we can yet understand. If you squint just right, metaphorically speaking, you might begin to see the universe not as a great machine built of matter, but as something altogether stranger. Not atoms and particles, but bits, ones and zeros. Some physicists, philosophers, and computer scientists are beginning to wonder, what if the fundamental layer of reality isn't stuff at all, but information? At first glance, it sounds like the plot of a science fiction film, but the idea has more weight than it seems. Think about it. Every book, every conversation, every email, every brainwave, even every particle interaction can be described in terms of information, not just what something is, but what it tells us. And in physics, what something tells us often matters more than what it's made of. Let's begin with a rather curious example. Black holes. These mysterious cosmic creatures are known for one main party trick, swallowing everything that gets too close, including light. But in the 1970s, Stephen Hawking and Jacob Bekenstein uncovered something deeply unsettling. Black holes seem to have entropy, and therefore information. More importantly, they appear to encode that information on their surface area, not their volume. That is, the amount of information a black hole can contain depends on the size of its event horizon, not what's inside it. This became known as the holographic principle, and it has stuck around. The idea is that everything within a region of space could be described by information stored on the boundary of that space. Just like a hologram, a three-dimensional image projected from a two-dimensional surface. If this holds true across the universe, then reality itself might be, at heart, a projection of underlying informational rules. Now that doesn't mean we live inside a literal hologram, or that you're secretly made of shimmering pixels. It's more subtle than that. It suggests that space and time themselves might emerge from something more fundamental, and that something could be information. But what does information mean here? In the broadest sense, it's the resolution of uncertainty. It's the difference between a flipped coin showing heads or tails. It's the pattern in the static, the shape in the chaos. In physics, information describes the state of a system, where particles are, how they move, how they spin. Every change, every law, every interaction is a kind of communication between parts of the universe. Now enter Claude Shannon, the father of information theory. Back in the 1940s, Shannon was trying to figure out how to send messages reliably over noisy telephone lines. He ended up inventing a whole new mathematical framework for thinking about data, signals, and error correction. What he probably didn't expect was that decades later, his ideas would sneak into black holes, quantum mechanics, and the very foundations of physics. One of the big puzzles in modern physics is reconciling general relativity, which is all about geometry and smooth curves, with quantum mechanics, which is jittery, probabilistic, and fond of paradoxes. And it turns out that information might be the key. Quantum systems are inherently informational. You can't fully describe a quantum particle without talking about probabilities, measurements, and what you know, or don't know, about it. And here's the kicker. When you entangle two particles, information about their combined state becomes spread across both of them, no matter how far apart they are. That sounds like magic, but it's real, and it's telling us something. Information might be more foundational than matter itself. Some researchers have taken this idea and run with it. There's a growing school of thought, sometimes called digital physics, or it from bit, which suggests that reality is essentially computational, not necessarily like a laptop running Windows, but like a vast, abstract processing system. The physicist John Archibald Wheeler, who coined the phrase it from bit, believed that every particle, field, or event in the universe ultimately derives from binary yes-no choices. Everything arises from an answer to a question, whether a photon was detected, whether an electron took one path or another. In this view, the universe is less like a collection of marbles and more like a flowing river of data. Matter and energy are just the higher-level outputs of a deeper rule-based computation. Now let's be careful here. Saying the universe is a computer doesn't mean it has a motherboard and a power cord, but it might mean that it operates as if it were computing, that every interaction, every ripple of a field, every gravitational tug is a processing of information according to physical rules. Even the laws themselves might be encoded. Constants like the speed of light, Planck's constant, and the gravitational constant could be not just features of reality, but lines in the ultimate cosmic software. There's also a very practical side to all this. The field of quantum computing is based on treating particles as information processors. Qubits, quantum bits, can represent a 0, a 1, or both at once thanks to superposition. And when entangled, they create correlations that can't be explained by classical physics. These principles aren't science fiction. They're real, and we're building machines based on them. Machines that hint at how deeply woven information is into the nature of reality. Some physicists go even further, wondering whether space itself might emerge from information. That the geometry of spacetime could arise from patterns of entanglement, like a spiderweb knitting itself from the inside out. In this picture, space isn't a backdrop, it's a consequence. If that's true, then asking where something is might be less important than asking how it relates to everything else. Distance, location, even direction could be less fundamental than the network of informational connections that link things together. You're not just here, you're entangled here, related to everything around you by shared information. It's dizzying stuff, but also oddly peaceful. Because if information is the true currency of the cosmos, then everything that happens, every flicker of thought, every falling leaf, every collapsing star, is a meaningful transition in an ever-evolving story. Nothing is lost. It's just transformed, encoded, passed along. This leads to a curious reflection on life itself. Your brain isn't just a lump of matter. It's an information processing system of staggering complexity. Your thoughts, memories, feelings, they're not made of atoms. They're patterns in the dance of atoms. They're information structured and animated. And maybe that's true of the universe too. Maybe the galaxies and stars, the laws and constants, are just the outer crust of something deeper, a cosmic language, always speaking, always computing, always unfolding. Of course, this idea still lives on the speculative edges of physics. It's bold, it's new, and it's not yet proven. But it's gaining traction because it helps make sense of things that traditional physics struggles with. And it reminds us that reality might be less like a rock and more like a whisper. So as you drift into stillness, let this thought linger. Perhaps the universe isn't made of hard edges and heavy things, but of gentle distinctions, quiet changes, and bits of information passing through the dark. Perhaps we're all part of a cosmic computation, an elegant, lawful, meaningful flow of bits becoming patterns, becoming stories, becoming the stars. You're not a random arrangement of matter. You're information, shaped by laws, unfolding through time. And maybe, just maybe, that's the most real thing of all. There's a curious thought experiment floating around in modern physics and philosophy circles. It's not about time travel or wormholes or parallel universes, though it does carry a pinch of all three. It goes like this. If the universe behaves like a program, could it actually be running one? Could the laws of nature be more than just laws? Could they be code? And if so, who or what is doing the computing? Now, before we slide too far down the digital rabbit hole, let's take a breath. The idea that the universe might be a simulation has been popularized in sci-fi stories and internet forums, but the version we're exploring tonight is subtler. It's not necessarily about alien teenagers running reality on a cosmic gaming PC. It's about whether the universe behaves as if it were calculating itself into existence. Let's start with a humble observation. The laws of physics are weirdly consistent. Gravity pulls the same way in Canada as it does in deep space. The speed of light is constant whether you're chasing a photon or sipping tea in your garden. Atoms click together in predictable ways. Equations like Schrödinger's or Einstein's seem to describe reality with eerie precision. This kind of consistency, this repeatability, is exactly what makes something programmable. If a system has rules, and those rules can be applied repeatedly to get reliable results, that's not unlike how algorithms work. You give them inputs, they give you outputs, you feed in the current state of a particle, and the rules tell you the next likely outcome. And here's the kicker. The more we study reality, the more it behaves like a processing engine. Not in the sense of flashing LEDs and silicon chips, but in the abstract way information flows and transforms. A simple set of starting conditions plus a clear rulebook can lead to immense complexity. Just ask cellular automata. Cellular automata are little computer programs that simulate how simple units, like pixels or cells, behave over time according to rules. One of the most famous is called Conway's Game of Life. In this system, tiny squares live or die depending on the number of neighbours they have. That's it. Just that one rule. And yet from this basic setup you can get astonishing patterns, self-replicating shapes, stable structures, even things that look like they're moving. It turns out you can simulate logic, build calculators, even construct full computers inside this tiny sandbox. From the simplest rules emerge incredible behaviours. Sound familiar? This resemblance has led some researchers to ask, what if the universe itself is a kind of cellular automaton? What if the particles, fields and forces we see are just emergent outcomes of a deeper rule-based structure? Not simulated in the traditional sense, but computed from within. Self-contained, self-executing. This idea goes by many names: digital physics, computational universe, algorithmic reality. The underlying concept is that reality is not continuous but discrete. That space and time, rather than being smooth and unbroken, are made up of tiny indivisible units, like pixels in a screen or bits in a file. At the smallest scales, perhaps the Planck length or the Planck time, the universe may tick, processing one frame of existence into the next. No one has found definitive proof of this, yet, but the search is on. Some physicists are investigating whether high-energy particles exhibit jitter or graininess that would hint at a digital substrate. Others are testing quantum systems to look for telltale signs of algorithmic limits, and still others are using black hole thermodynamics and holographic models to probe whether space itself encodes data like a hard drive. What makes this whole line of thinking even more deliciously strange is that it offers an answer to a long-standing puzzle. Why are the laws of physics so elegant? Why do they work with such mathematical beauty? Why is the universe understandable at all? If you ask a programmer to write a system that generates galaxies, stars, life and thought, they'll probably try to do it efficiently. With minimal code, elegant recursion, and reusable rules. The simpler the algorithm, the more scalable the simulation. It's not hard to imagine that a universe based on code might be one where simplicity and elegance are survival traits. But wait, does that mean we're living in a simulation? Not necessarily. The term simulation implies that someone or something outside the system is running it, that we're inside a computer with an exterior observer watching us. That's a bold and untestable claim. What we're talking about here is different. It's more like saying the universe is a computation unto itself. No external hard drive, no cosmic keyboard, just a self-running, rule-following system that happens to look a lot like a simulation. It's a subtle but important distinction. We don't have to believe in a programmer to believe in computation. After all, snowflakes compute their own patterns from temperature and humidity. Crystals compute their shapes based on bonding rules. The brain computes thoughts from electrochemical signals. Perhaps the universe, at its deepest level, is computing itself. Another perspective comes from quantum mechanics, where particles seem to decide how to behave only when measured. In this view, reality is not a fixed film reel, but an evolving script, written and revealed line by line. The act of observation updates the state of the universe, like a line of code running only when called. This isn't exactly simulation theory, but it is suggestive of a world that unfolds according to context, not absolute predefinition. So what would it mean if this were true? If the universe is running on rules that resemble code, what does that change? Well, for starters, it might explain why mathematics is so effective at describing the universe. Equations aren't just tools. We may be uncovering the very operating system of reality. It could mean that matter, space, and time are secondary to relationships, logic, and state transitions. That causality is the core, and everything else is emergent. It might also help unify the messy corners of physics, the way quantum randomness and general relativity's determinism still haven't shaken hands. If there's a shared algorithm underneath both, perhaps we'll eventually decode it. Not with telescopes or microscopes, but with logic, pattern recognition, and clever thinking. Of course, this is still speculative. Elegant, yes. Intriguing, certainly. But unproven. The universe hasn't handed over its source code just yet. And there are good reasons to be cautious about anthropomorphizing it with digital metaphors. Just because we build computers doesn't mean the cosmos is one. But what a thought. A reality that updates itself frame by frame, not from outside, but from the bottom up. No operator, no simulator, just a breathtakingly vast, self-consistent system of patterns unfolding according to timeless laws. In a way, whether or not the universe is simulating itself may be less important than the fact that it can be understood as if it were. And that's what makes physics feel almost poetic. We aren't decoding chaos. We're listening to structure. We're watching the dance of algorithms in the dust of stars. So as you settle deeper into rest, imagine the universe quietly updating itself. Not as noise, but as a soft and infinite rhythm. Not as a machine, but as a symphony of logic. You, me, everything. Part of a grand equation that writes itself with perfect grace. Not simulated, just rule-bound. Wonderfully so. Imagine waking up in a world with no objects, no particles, no things, just connections. No chairs or trees or atoms, but only the web of relationships that tell us how one thing is linked to another. It sounds abstract, almost like a thought puzzle. But according to some of the deepest thinkers in modern physics, this may not be far from the truth. Let's take a gentle step into this curious idea that the universe is not made of things, but of the relationships between things. That the rules matter more than the players. That what we call reality might be less like a collection of Lego blocks and more like the invisible threads that hold a spiderweb together. Delicate, patterned, and wholly dependent on context. This concept is known as relationalism. It has roots going back centuries, debated by philosophers like Leibniz and Mach. In their view, space wasn't a container that things sat inside. Rather, space was the set of relationships between objects. Take the objects away and space ceases to exist, not because it's empty, but because it was never a thing in the first place. This is a huge departure from the way most of us think. We're used to picturing particles flying around in a kind of cosmic stage. They have positions, they have mass, they interact. But the relational approach says, no, you're missing the point. What really matters is how they interact, not that they exist. A particle has no location unless it's in a relation to something else. No mass unless it resists a push. No identity unless it does something observable. Quantum mechanics, strange and spooky as it can be, seems to back this up. In quantum physics, particles don't even have definite properties until they're measured. Before observation, they exist in a haze of possibilities, a probability cloud. Their characteristics emerge only when they interact. In other words, what something is depends entirely on how it's related to everything else. And that's not just poetic, it's testable. One famous example is the quantum entanglement experiment. Take two particles that interact, then send them to opposite ends of the galaxy. Measure one, and the other's state becomes instantly defined. They're not separate entities, they're a system. Their connection matters more than their individual identities. The universe seems to care more about the relationship than the pieces. This leads to a startling but oddly elegant idea. Maybe the universe is a network, not a collection. Not a bag of marbles, but a web of meaning. Each point is defined only by its connection to others. It's not the dots that matter, but the lines. Carlo Rovelli, one of the leading proponents of loop quantum gravity, has taken this to heart. In his view, even space-time itself might be a product of relationships. Not a smooth, flowing fabric, but a granular mesh of tiny connections, constantly updating. In his theory, the geometry of space isn't fundamental. It's woven from the quantum interactions of loops. No background, no canvas, just the dance of loops, forming reality through their interconnections. It's a little like a conversation. The meaning isn't in the words alone, but in how they relate to one another. You can't understand a single word in isolation. It only gains meaning when placed in context, in relationship with the words around it. Reality perhaps works the same way, and this idea doesn't stop with space and matter. Time too might be relational. In our everyday lives, time feels absolute. We count seconds on a clock, watch the hands move. But according to relativity, time is entirely dependent on your frame of reference. Two observers in different places can experience time differently. There's no universal now, only relationships between moments, measured from different perspectives. It's like the universe is whispering. There are no absolutes here, only context. Now, this might sound unsettling at first. We like our objects. We like knowing that the coffee mug is there, that the planet exists, that the moon is still circling. But relational thinking doesn't take those things away. It just changes how we understand them. The moon is real, but its reality is defined by how it moves, pulls, reflects, and glows in our sky. The mug is real, but only because it holds liquid, resists gravity, and clinks on your desk. Things don't exist in isolation. They exist in relation. This isn't just theoretical musing. It's increasingly relevant in fields like quantum gravity, string theory, and quantum information. Many of the problems physicists face, like combining general relativity with quantum mechanics, might be easier to solve if we let go of the idea of absolute space and time, and instead focus on the interactions, the relationships, the ever-changing web. It's even showing up in cosmology. When we ask, what happened before the Big Bang, we're asking a question that might not make sense. Time, space, causality, these may not have existed independently. They may have emerged from a more fundamental relational structure. In that primordial state, there were no things, just potential, just relationships, waiting to bloom into galaxies and planets and sleepy humans pondering physics in bed. And what about you? Well, even you are a network, not just of cells and synapses, but of memories, conversations, dreams and choices. You're not a fixed object, but a shifting story, a set of relationships that evolve every day. Your identity doesn't live in your atoms, it lives in the pattern they form, in how you feel, think, and connect. So maybe the universe isn't a machine of parts, but a poem of context, a conversation with itself, shaped by the relationships that arise and dissolve, a web of meaning spun from the invisible tension between what could be and what is. It's a comforting thought in its own quiet way, because it means that nothing is ever truly isolated. Not a star, not a thought, not a person. We're all part of the same great tapestry, not as separate threads, but as crossings, connections, echoes of one another. As you drift deeper into rest, let yourself feel that soft entanglement. You're here not because of what you are, but because of how you relate to the stars above, to the ground below, to the voices you've heard and the lives you've touched. In this relational universe, existence is not a solitary event. It's a dance, a web, a whisper between neighbours across the void, and it never stops moving. There's a kind of magic in tracing back the shape of your thoughts to the quiet structure of the cosmos. Not the stage of stars and galaxies, but the rules, the laws that govern motion, matter and energy. They didn't plan anything. They have no intentions, no preferences, and yet here you are, thinking, remembering, perhaps yawning gently as your eyes grow heavier. How does that happen? How do blind, unfeeling laws give rise to living things? To a creature who can look up at the stars and wonder about the very laws that allowed them to form. Let's begin not with life, but with gravity. Gravity doesn't care about life. It pulls indiscriminately. But because it pulls, gas clouds collapse. Because they collapse, stars ignite. Because stars shine, they forge elements. And because those elements scatter when stars die, they can be swept up again into new stars, planets, and eventually the chemistry of biology. Carbon didn't know it would end up in a brain. Oxygen had no ambition to be breathed. But the rules of the universe, the equations that guide energy and matter, created the conditions for complexity. They built layers of stability. They allowed structure to persist just long enough to try something new, over and over again. The early Earth was a churning, hostile place. Volcanoes rumbled, lightning danced, comets crashed into the oceans. Yet inside this chaos, something profound began to stir. Simple molecules bumped and bounced, and under the guidance of chemical laws they began to form chains. These chains copied themselves, interacted, folded and evolved. No miracles, no need for anything beyond physics and chemistry, just persistence, just the quiet favouring of patterns that stick around longer than others, and eventually, life. The first cells didn't know they were alive, but they obeyed the rules. Diffusion, membrane gradients, molecular bonding. Through sheer trial and error, they found ways to survive. And as billions of years slipped by, those cells changed. They combined. They formed networks. They discovered sight, motion, even a crude form of memory. Still no intentions, still no guiding hand. Just the slow dance of possibility and law. One rule allowed energy to be stored. Another rule allowed it to be released. And with each small success, life grew bolder, more intricate, more aware. Then came the neuron. The neuron is one of the most extraordinary accidents in the universe. A single cell shaped by evolution, capable of transmitting information through tiny electrochemical pulses. Not just reacting to the world, but encoding it, forming networks, talking to other cells, storing impressions of experience. You might say neurons are where rules became reflex, where chemistry became behavior, where action met memory and forged something entirely new, the mind. From those early neurons came brains. From brains came thoughts. From thoughts came stories, tools, and language. The ability to imagine, to plan, to wonder about distant places and times. The ability to reflect on the laws that built us. And all of this, every dream, every memory, every quiet moment under the stars, is the echo of physical laws playing out in exquisite complexity. You're not apart from the universe. You're not merely in it. You are of it, made by it, a walking testament to its possibilities. It's tempting to think of laws as limits. Gravity restricts, thermodynamics demands, entropy erodes. But in truth, laws are enablers. Without rules, there is no coherence. Without structure, no order. It is the constraints that create the space for meaning to emerge. Imagine a world without rules. No gravity, no electromagnetic forces, no chemical bonds. It wouldn't be wild. It would be silent, lifeless, a fog of nothing. No atoms, no stars, certainly no beings curled up under a blanket listening to a sleepy voice ponder the origins of thought. Rules make the universe possible, and they don't stop at the edge of the cosmos. They continue, delicately and unceasingly, in your bloodstream, in your cells, in your thoughts. Your body obeys gravity. Your neurons obey electrochemical gradients. Your memories are patterns held in networks of molecules, shaped by the same logic that spins galaxies. When you see a flower bloom, you're witnessing molecules arranging themselves in perfect obedience to thermodynamic pressures and genetic blueprints. When you fall in love, hormones rise and neurotransmitters light up in perfect response to cues shaped by millions of years of biology, itself shaped by particles, stars, and the deaths of suns. It's all connected. Even consciousness, that slippery marvel, may not be an exception. Some believe it arises from information processing in complex systems, a natural extension of physical rules. Your awareness, fleeting and precious, may be the product of patterns rich enough to loop back on themselves, to reflect, to narrate, to wonder. The laws of nature didn't know they would do this. They didn't set out to build creatures who ask questions. But when matter plays by the rules long enough, sometimes it builds something that starts to ask why. Something that can hear a phrase like laws of physics and respond not with indifference, but with curiosity. And here's the gentle truth. None of this had to happen. The universe could have fizzled out in chaos. It could have expanded into sterile silence. But instead, it built stars and planets and rain and music and stories and listeners. Listeners like you. You're a collection of particles obeying ancient rules, but you're also more than that. You're the living expression of those rules, the point where equations become experience, where energy becomes thought, where law becomes life. So as you settle into sleep, know that the atoms in your pillow once burned in a star, that your breath is shared with trees, your heartbeat echoes ancient rhythms, your mind is stitched from the quiet logic of the cosmos. The universe didn't just give you a place to be, it gave you the ability to be, and through you its laws remember themselves, not in silence, but in awe. And so we come to the end of our quiet journey. Through gravity and neurons, through constants and questions, through the invisible architecture of everything. Perhaps the universe isn't made of stuff after all. Not really. It's made of patterns, of balance, of quiet, persistent, elegant rules that never sleep. Laws that don't shimmer or sing, but hold the very fabric of being in place. Laws that allowed hydrogen to burn, planets to form, and minds to wonder. Laws that made it possible for you to be here, listening, drifting. You're not separate from those rules. You are one of their outcomes, one of their most astonishing poems. And before you close your eyes, I'd love to ask again, where in the world are you listening from tonight? And what time is it for you right now? Leave a little note in the comments if you feel like it. I read every one. And if this video brought you a moment of calm, a spark of curiosity, or simply helped you wind down after a long day, I'd be so grateful if you tapped that like button, or even subscribed. It helps this sleepy little channel find more dreamers just like you. Sleep well, fellow traveller. The universe is still humming. Let it carry you.